Tonight, we're going to rewind the universe to a time so small it barely counts as a time at all. About 10 to the power of minus 43 seconds after the Big Bang, 1 Planck time. In that instant, the entire cosmic mission either locked in the rules that would one day let you breathe, think, and watch this video, or failed, and erased any chance of observers forever. Before we get started, imagine the universe as a coin being flipped once at the very beginning. Not a normal coin. This one encodes gravity, the expansion rate, the balance between matter and antimatter, and the quantum seeds of every galaxy that will ever exist. If the heads side lands with those values off by as little as 1 part in 10 to the power of 60, there are no planets, no chemistry, no solar system, and no one to notice that anything went wrong. Scientists call this the era when space, time, and the fundamental forces first separated and solidified. To human intuition, it looks like chaos. An explosion, unimaginable temperature, a violent wind of particles and radiation. But from the perspective of physics, something incredibly precise had to emerge from that chaos. The density had to sit almost exactly on a razor's edge between too much and too little. The expansion had to outrun gravity without escaping it, and matter had to win a tiny victory over antimatter by roughly 1 particle in a billion. So, picture 3 universes branching from that 10 to the minus 43 second coin flip. In the first, gravity is just a little stronger, or the early density just a little higher. The whole system collapses back on itself almost immediately, forming a uniform fog of black holes with no stars, no light, only a dark, crushing boundary from which nothing can escape. In the second, expansion races ahead. Space stretches so fast that matter never clumps. No galaxies, no stars, only thin, cold nothingness expanding beyond any hope of structure. And then there is the third universe, this one, where expansion and gravity nearly cancel, but not quite, where tiny ripples in the early plasma grow into galaxies, where stars forge heavy elements, where planets condense, and where, on at least one small world, a technological species builds spacecraft and wonders why the coin landed this way. No one expects an apparently chaotic blast to produce a cosmos that looks so exquisitely arranged for life. No one predicts that almost every parameter at the beginning would sit in a narrow, just right range. Yet that is exactly what seems to have been discovered. Now, let's begin. Tonight, we're going to treat the entire observable universe as a crime scene, a forensic investigation into fine-tuning. Step by step, from that first 10 to the power of minus 43 seconds to the formation of stars, planets, and eventually you. The goal is to understand whether this perfection is real, an illusion, or evidence of something stranger lurking beyond our cosmic horizon. By the end of tonight, you're going to understand why nearly everything you see in the night sky, the galaxies, the stars, even our moon, depends on that first coin flip landing in a shockingly narrow range, and what it would have meant if it hadn't. From a distance, it does not look perfect at all. The universe looks violent, wasteful, and indifferent. Space is littered with dead planets, collapsing stars, and black holes that erase anything crossing their boundary. Supernovae rip apart entire solar systems. Galaxies crash through each other in slow-motion collisions. Most planets discovered so far are scorched gas giants grazing their stars, frozen worlds drifting in the dark, or rocky spheres with no air, no oceans, no chance. If this is a precision-tuned mission for life, it hides that intention behind a mask of chaos. And yet, underneath that chaos, the numbers look absurdly precise. The cosmological constant, the tiny term that controls how fast space itself accelerates, appears tuned to about 1 part in 10 to the power of 120. Increase it slightly, and the universe expands so fast that galaxies never form. Decrease it too much, and gravity wins early, pulling everything back into a dense fireball before stars can ignite. Gravity's strength is another razor's edge. Dial it up by roughly 1 part in 10 to the power of 60, and the universe collapses in on itself long before planets can assemble. Dial it down and matter never clumps. No stars, no galaxies, just a thin, cold fog, expanding forever. The strong nuclear force walks a similar line. A few percent weaker, and only hydrogen exists. A few percent stronger, and almost all hydrogen fuses away in the early universe, starving future stars of the fuel they need to shine for billions of years. Then, there is the initial expansion. Right after the Big Bang, the density of the universe had to match a critical value to within about 1 part in 10 to the power of 60. Too dense, instant recollapse. Too thin, runaway expansion with no time to build complex structure. The same explosion that almost tore the universe apart is the only reason the heavy elements in your body exist at all. And this fine-tuning does not stop at the cosmic scale. It follows down into our own system. Earth orbits a long-lived, stable star with just the right mass to burn calmly for billions of years. Our planet sits in a narrow habitable zone where water can remain liquid. An unusually large moon stabilizes Earth's axial tilt, preventing wild climate swings that could erase complex life. Plate tectonics, a protective magnetic field, and a thick, balanced atmosphere all conspire to keep the surface temperate and chemically active. So, what is going on here? Are you the outcome of a 1 in a trillion cosmic lottery, a lucky draw from a vast ensemble of possible universes? Is there a deeper law, still hidden from scientists, that forces these constants and conditions to land in the life-friendly range? Or is there something off about the way the question is even being asked? Before we get started on answers, there is one idea that seems trivial at first, but refuses to go away. It is called the Anthropic principle. In simple terms, the universe looks compatible with life because if it did not, no one would be here to complain about it. On one level, that sounds obvious, almost empty. On another, it feels less like an answer and more like a riddle about observation, probability, and what it means to exist in the first place. Tonight, we're going to peel this riddle apart in layers. First, the largest scales. The Big Bang, the expansion of space and the fundamental forces, then stars and galaxies and how their violent lives accidentally create habitable islands. Then the peculiar engineering of Earth and its moon. Finally, the boldest attempts to explain it all. Anthropic reasoning, multiverse ideas, and the possibility that the universe had to be perfect, or that perfection is an illusion. Now, let's begin with the moment the universe had just 10 to the power of minus 43 seconds to get everything right. Now, let's begin with the moment the universe had just 10 to the power of minus 43 seconds to get everything right. This is where many space videos would zoom out, show a gorgeous star field, and remind you that the universe is very big and very old. Impressive? Yes. But size and age alone do not get you chemistry, consciousness, or a solar system that can build radio telescopes and wonder what went wrong in the first microsecond. Tonight, we're going to look at something sharper. the knife edge between a dead cosmos and one that can ask questions about itself. Most documentaries stop at awe. Vast distances, beautiful planets, a heroic spacecraft or two sailing beyond the boundary of the known. Here, the mission is different. The focus is on the numbers under the scenery, the strength of gravity to 1 part in 10 to the power of 60, the cosmological constant balanced to about 1 in 10 to the power of 120, the early density fluctuations tuned so galaxies can condense but do not instantly collapse. Change those just a little, and every star, every planet, every breath you take disappears from the script. This episode is for a particular kind of viewer, the one who stays up too late reading about black holes evaporating over trillions of years, who dives into quantum mechanics threads that leave the browser full of tabs and the brain full of questions, who wonders whether the Fermi paradox is a clue about our own fragility. If that sounds familiar, you are not alone. There is an entire quiet community orbiting the same questions. Why does this universe make observers at all? And what happens if even one constant drifts? Before we get started on the detailed physics, a quick request. If deep dive, long-form explorations of space, physics, and the strange fact of our own existence are the kind of thing that pull you in, consider tapping like or subscribing. It is a tiny action, but it changes what the algorithm thinks the mission should be. Here is why that matters, without guilt. When a video like this gets comments, likes, and shares, the platform discovers that there are more curious minds out there than anyone expects. No one predicts that a 40-minute breakdown of cosmological fine-tuning will compete with short clips and highlight reels, yet sometimes it does. And absolutely no one anticipates how much easier it becomes to justify ambitious, research-heavy episodes when the signal from viewers is loud and clear. In return, the promise is simple. The same care that scientists use to measure the solar wind or map the edge of the heliosphere goes into tracing how each constant, each early fluctuation, each planetary coincidence stacks together. By the end of tonight, you're going to understand why tiny numerical tweaks decide whether there are galaxies, oceans, or questions. So now, rewind. Strip away planets, stars, even atoms. Run the clock back until there is only an expanding, blazing plasma and a handful of numbers written into the laws of physics. From here on, the task is to watch those numbers decide whether anything interesting will ever happen. For most of the 20th century, that blazing plasma had a very simple origin story. The traditional Big Bang picture goes like this: everything in space all at once compressed into a state so hot and dense that atoms could not exist, then suddenly expanding, cooling, and thinning out over billions of years until the first neutral atoms, the first stars, and the first galaxies took shape. In this view, you are living in the faded afterglow of a single titanic event. Space itself stretches. The solar system, the planets, and every galaxy are carried along like raisins in rising dough. As the universe expands, the fireball cools from white-hot radiation to a seething plasma, then finally to a transparent cosmos where light can travel freely. That ancient light stretched by expansion into microwaves is the cosmic microwave background, a nearly uniform bath of radiation filling all of space. By the mid-1960s, scientists thought the broad strokes were nailed. The universe expands. The rate of that expansion is encoded in a single number, the Hubble parameter. The leftover heat from the Big Bang shines as the microwave background. With those ingredients, cosmology looked almost tidy. The early conditions, those could be messy, even arbitrary, without obviously wrecking the story. So the key parameters were treated like dials on a control panel. The overall density of the universe, the exact expansion rate, the mix of radiation, ordinary matter, dark matter, and, later, dark energy. Change a dial, the thinking went, and you might get a universe with more galaxies or fewer older stars or younger ones, but still a universe. Still some kind of cosmic landscape where something could exist. Before we get started on how wrong that turned out to be, picture a kitchen. The early universe was often compared to baking bread. You set an initial temperature, choose how much yeast to add, decide how long to bake. Too cool, the dough barely rises. Too hot, it burns. But within a wide range, you still pull some kind of loaf from the oven. By the end of tonight, you're going to understand why cosmology moved from some kind of loaf to hit these numbers or you get no bread at all. At first, no one expects those dials to be fragile. No one predicts that the overall density must be tuned to within about 1 part in 10 to the power of 60 of a critical value, or expansion either recollapses the universe or tears it apart before galaxies form. Absolutely no one anticipates that dark energy's strength, the cosmological constant, has to sit in a range so narrow that changing it by about 1 part in 10 to the power of 120 would erase every galaxy in space. Then the measurements sharpen. Galaxy surveys map the large-scale structure of the cosmos. Satellites like COBE, WMAP, and Planck turn the microwave background from a fuzzy glow into a precision map, measuring tiny temperature ripples across the entire sky. Expectation meets reality, and the contrast is brutal. The universe is not running on loose settings. It is running on a recipe balanced on a knife edge. And the closer those instruments look at that first fraction of a second, the more that knife edge begins to look impossibly thin. Now, let's begin to ask what happens if any of those early dials move, even slightly, and why that matters for oceans, chemistry, and you. If those early dials can move, one of them is more dangerous than all the others combined. It is the one that decides whether the entire mission of the universe ends in an instant crash or drifts into a cold, empty failure. The total density of everything in space and how fast that space is expanding. Think of it this way: throw a ball upward, too slow, and gravity pulls it back. Too fast, and it escapes forever. There is a razor-thin speed where it rises, slows, and never quite falls, but never quite gets away. Cosmologists discovered that the universe has an equivalent setting called the critical density. It is the precise balance where the gravity of all matter and energy is just strong enough to slow the cosmic expansion, but not strong enough to drag it all back into a catastrophic big crunch. Now, let's begin to see how tight that balance really is. At about 1 second after the Big Bang, the actual density of the universe had to match this critical density to within about 1 part in 10 to the 60th. That is a 1 with 60 zeros. Add just a whisper more density and gravity wins early. The universe recollapses long before the first star can ignite. Subtract just a whisper, and expansion races ahead. Matter thins out so fast that galaxies never condense at all. Tonight, we're going to imagine that as a cosmic slider labeled density. Slide it from left to right, from universes that crunch to universes that rip apart. The life-friendly zone is not a comfortable band. It is thinner than a single atom compared to the width of the observable universe. If the whole visible cosmos were stretched across your screen, the range that allows long-lived stars would be a region narrower than a pixel, sitting in the exact middle. And that tiny window controls everything down here. Without that near-perfect critical density, there are no galaxies with orderly spiral arms, no long-burning suns like ours, no stable planetary systems with decades, let alone billions of years, for chemistry to experiment. There is no time to forge heavy elements in stellar cores and supernovas, no way to build carbon chains, oceans, atmospheres, or the electrical storms inside a brain. The entire solar system is riding on a number set with absurd precision, long before the first planet existed. By the end of tonight, you're going to understand why this shocked scientists. Random initial conditions should spray out universes that either collapse almost instantly or blow apart into a thin, dark haze. No one expects the density to land so perfectly on the knife edge that allows galaxies. No one predicts a cosmos that behaves as if it were driven toward this critical balance on purpose. That eerie coincidence was one of the first clues that something deeper, like a brief, violent era of cosmic inflation, might be sculpting the entire playing field. And when that idea arrives, the picture of fine-tuning becomes even stranger. That deeper structure is not just about how space expands. It is about what holds you together right now. Your bones, your blood, the device in your hand, every atom in the solar system is balanced on 4 invisible interactions, each with a strength that could have been different. Change those numbers even slightly, and the entire mission of the universe changes with them. Tonight, we're going to stand on that boundary and look at the forces themselves: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. 4 interactions, 4 dimensionless strengths, written into reality long before planets, spacecraft, or scientists existed to measure them. By the end of tonight, you're going to understand why there are no second chances if those values drift. Start with gravity, the quietest of the 4. On paper, it is absurdly weak. The electromagnetic force between 2 protons is about 10 to the power of 36 times stronger than their gravitational pull. That weakness saves you. If gravity were much stronger, stars would crush themselves quickly, burning through their fuel in frantic, brief flashes. Massive stars would collapse into black holes before complex chemistry had time to unfold on any world. If gravity were weaker, matter might never clump into galaxies at all. The early universe's tiny density ripples would just smear out, leaving only a thin, dark fog. Now, let's begin to zoom in. Inside every atomic nucleus, the strong nuclear force glues protons and neutrons together. Its strength is another pure number, and fine-tuning here is razor sharp. If the strong force were about 2% weaker, nuclei heavier than hydrogen would not bind. No carbon, no oxygen, no iron, no planets. If it were about 2% stronger, nearly all hydrogen would have fused into helium in the first minutes after the Big Bang. That early overreaction would leave almost no hydrogen for water, no long-lived hydrogen-burning stars like the Sun, and no extended era for life to experiment. Electromagnetism lives one level out, shaping atoms and chemistry. Its strength is encoded in the fine structure constant, roughly 1/137. Nudge that value and everything changes. Stronger electromagnetism would shrink atoms, pull electrons tighter, and make chemical bonds so fierce that complex, flexible molecules might never form. Weaker, and atoms would swell, bonds would loosen, and large molecules would fall apart under their own thermal jitter. In both directions, the delicate architecture of biochemistry collapses. Then there is the weak nuclear force, which sounds unimportant and is anything but. It governs certain radioactive decays and the reactions that turn protons into neutrons and back, both in the early universe and deep inside stars. If the weak force were much weaker, the early cosmos would have frozen in a different balance of hydrogen and helium, and stellar cores would struggle to ignite or sustain stable burning. Make it much stronger, and nuclear reactions in stars would race, altering how long they shine and how they forge heavy elements. Long-lived, steady stars like the Sun might never appear. No one expects four unrelated numbers to line up in a way that permits galaxies, planets, oceans, and observers. No one predicts that tiny percentage shifts would erase everything you see when you look up. And absolutely no one anticipates what happens when these forces are combined with one more improbable ingredient, a particular kind of star, at a particular distance, circling in a particular system that looks suspiciously like home. That suspiciously like home system hides one more twist. The universe didn't just need the right stars and planets, it needed empty space itself to behave in an almost impossibly delicate way. Tonight, we're going to look at the strangest lottery ticket in all of physics, a number that decides whether space gently nurtures galaxies or rips them apart before they can form. Before we get started, picture this. Take a box, pump out all the air, remove every atom, every speck of dust. Common sense says you now have nothing, a true vacuum. But scientists discovered that in our best theories, even that empty space still seethes with energy. Fields flicker in and out of existence, virtual particles appear and vanish. That leftover energy of the vacuum is what cosmologists call the cosmological constant. In plain language, it's a tiny energy built into space itself, spread everywhere, invisible but with real gravity. Instead of pulling like normal matter, it pushes, making the expansion of the universe accelerate. On cosmic scales, this gentle push is what is often called dark energy. Now, let's begin. Quantum field theory, the same framework that predicts the behavior of particles in accelerators and the interior of the solar wind, says that vacuum energy should be huge. Not a gentle nudge, a roaring flood. Add up all the modes of all the fields, and the naive prediction is that empty space should be packed with energy. So much energy that the universe should have blown itself apart almost instantly after the Big Bang. Here's the contrast. Expectation, a colossal vacuum energy, large enough to overwhelm gravity from every galaxy, every star, every planet. Reality, a cosmological constant so small that it only starts to dominate the expansion tens of billions of years into the mission of the universe. The mismatch is not a factor of 10. It's not a factor of 1,000,000. It's about 1 part in 10 to the power of 120. This is often called the worst prediction in physics. Pattern interrupt. 10 to the power of 120 is not just a big number. If every atom in the observable universe were a separate lottery, each with 1 trillion tickets, you would still be nowhere close. That is the precision with which this cosmic dial seems set. Now push it slightly. Make the cosmological constant just a bit larger. The expansion accelerates earlier. Matter never has time to condense. No one expects stable galaxies. No one predicts long-lived stars. Instead of spiraling solar systems, you get an ever-thinning, cold mist. No heavy elements forged in stellar cores, no rocky planets, no oceans, no observers to ask why. So, what is this? Are we unbelievably lucky to live in the one universe where this number lands in the razor-thin, life-permitting range? Or is the entire understanding of vacuum energy and gravity incomplete? By the end of tonight, you're going to understand why some scientists invoke a multiverse, and why others think a deeper principle is still hiding beyond our current horizon. So, if the vacuum energy looks impossibly tuned, maybe the early universe had a trick up its sleeve, a reset button. Tonight, we're going to step into the first sliver of a second after the Big Bang, when space itself may have done something so extreme it almost erased every trace of our existence before it began. Now, let's begin. Imagine space as a stretchy fabric. But for a brief instant it doesn't just stretch, it explodes in size. Not like a bomb in space, but space expanding everywhere at once. In less than a trillionth of a second, the observable universe balloons from subatomic scales to something far larger than all the planets and stars that will ever form. This is cosmic inflation, ultra-rapid expansion that takes whatever irregular, wrinkled initial conditions existed and smooths them out like a cosmic ironing pass. The payoff is huge. Before we get started on galaxies and life, the universe has a serious engineering problem: critical density. To form long-lived stars and stable solar systems, the average density of matter and energy has to sit within about 1 part in 10 to the 60 power of a special value. Too dense, and gravity wins early, pulling everything back into a fireball. Too thin, and expansion races ahead, leaving space almost empty, with no time to assemble planets. Inflation attacks this directly. As space inflates, any initial curvature or density deviation is diluted. Peaks and valleys in the fabric of space are stretched so wide they look flat. The result is a universe driven toward a near-critical, almost perfectly flat state. The kind of stage where galaxies and stars can actually form, but inflation does more than smooth. It seeds. At quantum scales, the field driving inflation isn't perfectly uniform. Tiny quantum fluctuations jitter its value from point to point. During inflation, those microscopic ripples get dragged outward by the expanding space, frozen in as real density differences on cosmic scales. Later, when the universe cools and the ordinary expansion takes over, those tiny overdensities act like gravitational magnets. They pull in matter, grow, and eventually become galaxies, clusters, and the vast web of structure. The pattern of hot and cold spots in the cosmic microwave background is a fossil map of those stretched-out quantum fluctuations. On paper, it sounds like a mission accomplished. A single mechanism that flattens the universe, sets the critical density, and plants the seeds for every solar system. But no one expects a free lunch in cosmology. The inflationary field itself has to have very specific properties. A potential energy landscape that lets it roll slowly enough to drive expansion, then end at just the right moment. The amplitude of those quantum ripples must fall in a narrow range, make them 10 times larger, and the early universe collapses into black holes and violent clumps. Make them 10 times smaller, and gravity never gains enough leverage to build galaxies at all. The same explosion that creates the conditions for life also has to be exquisitely tuned not to destroy those conditions. And then comes the twist absolutely no one anticipates at first glance. Many inflation models don't just produce one smooth universe, they naturally spill into a kind of eternal process where different regions stop inflating at different times. Each finished region becomes a pocket universe with its own realization of fields, constants, maybe even different effective laws. Our flat, structured, life-friendly cosmos could be just one bubble in a vast inflating sea. If that's true, the question shifts. Are we seeing deep necessity in the laws of nature, or are we simply living in one of the rare pockets where the cosmic lottery produced a universe that can look back and ask why at all? So, if our universe is just one bubble in a larger inflating sea, there's an even stranger question hiding underneath. Why is there anything here, in this bubble at all? Not galaxies, not planets, not life. Anything. Because by the rules of the Big Bang, there really shouldn't be. Now, let's begin. When the universe was a fraction of a second old, it was a seething, blinding plasma, where energy constantly turned into particles and antiparticles, matter and antimatter. Same mass, opposite charge, perfect mirror images. Every time one met the other, they annihilated in a flash of pure radiation. If nature had been perfectly fair, the Big Bang would have made equal amounts of both. Perfectly balanced, perfectly doomed. In that fair universe, each proton would have an antiproton twin, each electron a positron partner. They would collide, vanish, and leave behind a smooth ocean of light expanding into the dark. No atoms, no stars, just a fading afterglow, space without structure. A solar system could never form, planets would never exist. There would be nothing for any spacecraft to explore, and no scientists to wonder why. But that is not the universe you live in. Observation tells a different story. For roughly every billion antimatter particles in the early plasma, there were about 1,000,000,001 matter particles, one extra proton here, one extra neutron there, one lonely survivor for every billion perfect pairings. After the great mutual annihilation, that tiny excess, one part in 1,000,000,000, is all the matter that remains. Every galaxy in the sky, every star in the Milky Way, every atom in your body is drawn from that minuscule surplus. Tonight, we're going to sit with how absurd that is. Imagine a cosmic casino where matter and antimatter are created in nearly perfect pairs and then forced to collide. The house rules say they cancel out. The table should clear. Yet some hidden bias in the game ever so slightly favors matter. A difference of 1 in 1,000,000,000 tilts the outcome of the entire cosmos. No one predicts that such a microscopic imbalance will decide whether the universe ends as pure radiation or grows complex enough to ask questions. Physicists give this early universe cheating a name: baryogenesis. In broad strokes, it means that in the first instance after the Big Bang, certain reactions must have treated matter and antimatter differently. Symmetries that seem sacred in the equations, like CP symmetry, which links particles with their mirror image antiparticles, had to be violated. Some experiments with subatomic particles have discovered tiny CP violations in the solar system's laboratories, but not nearly enough to explain the full cosmic imbalance. Something happened out there, beyond current understanding, and the balance had to be exquisite. If that asymmetry were much smaller, almost everything would annihilate. The thin mist of leftover matter would be too sparse to collapse into galaxies under gravity's pull. No stars, no heavy elements, no chemistry complex enough to build cells. If it were much larger, the early universe would be choked with the matter, changing how the primordial elements formed, altering the timing of star birth, reshaping the entire thermal history. The same fine-tuned nuclear reactions that built carbon and oxygen in stellar cores might never proceed in the familiar way. By the end of tonight, you're going to understand that you are made of statistical flukes that refused to cancel out. Every breath you take depends on a 1 in a billion preference written into the first microseconds of time. The universe ran a nearly perfect accounting of matter and antimatter and left just enough of a rounding error to write you into existence. But that was only the opening move, because even with this fragile dust of surviving matter, something else had to go right. The way that dust clumped, the way gravity pulled, and the way the cosmic expansion walked a knife edge between collapse and emptiness. And absolutely no one anticipates how tight that balancing act had to be. That balancing act shows up most clearly in one of the quietest, strangest images in all of science, a map of microwaves. The cosmic microwave background is not a pretty picture of planets or glowing nebulae. It's a baby photo of the entire universe, taken when it was only 380,000 years old, still a hot, glowing plasma, but just cool enough for light to finally travel freely. To the naked eye, that ancient light looks uniform, the same in every direction, a perfect fog. But when spacecraft like COBE, WMAP, and Planck sharpen the view, something shocking appears. Tiny blotches, minuscule temperature variations, only about 1 part in 100,000 across the sky. That's a change of a few hundred microkelvin on a background of 2.7 Kelvin. Almost nothing. And yet those barely there speckles are the fingerprints of tiny density differences in the early cosmic plasma. Now, let's begin. Because those small differences were everything. Regions that were just a little denser had just a little more gravity. That extra pull made them slow the expansion locally, tugging in more matter, while slightly emptier regions lost out. Given hundreds of millions of years, that tiny head start snowballed. What began as a 1 in 100,000 bump in density grew into clouds, then galaxies, then clusters, then the vast cosmic web spanning billions of light years. Here's the twist. That initial bump size, the amplitude of those ripples, could not be arbitrary. If the early universe had been smoother, with fluctuations 10 times smaller, gravity would never have caught up. Expansion would win everywhere. Matter would stay almost perfectly spread out, no galaxies, no stars, no planets. Just a thin, cooling fog of hydrogen and helium stretching into the dark. But if the ripples had been 10 times larger, the opposite disaster unfolds. Overdense regions would collapse so quickly and violently that they'd skip the gentle phase of star and galaxy formation. Black holes, dense clumps, and short-lived monster stars would dominate. Long-lived, stable suns like the one at the center of this solar system would struggle to exist at all, and the quiet, billions of years window needed for complex chemistry and life would slam shut. There is another invisible player in this drama. Dark matter. It doesn't glow. It doesn't absorb light, but it responds to gravity, and it was already clumping while ordinary matter was still locked in that hot plasma. Those same tiny ripples in the microwave background trace dark matter's scaffolding. It provided extra gravitational pull, deepening the wells that baryonic gas could later fall into once the universe became transparent. Without that hidden mass, structure would form too slowly. With too much, it would form too fast. Tonight, we're going to treat those speckles as clues, because their strength, their pattern, and their scale line up eerily well with what inflationary models predict. quantum jitters stretched to cosmic size. By the end of tonight, you're going to understand why no one predicts, and absolutely no one anticipates, that a universe tuned for life would also look exactly like the output of a blind, violent, exponential expansion. So how did the cosmos set those initial ripples to just the right amplitude? And what does that say about everything that came after? Those tiny quantum ripples give you galaxies, but galaxies alone don't give you life. Tonight, we're going to shift from the architecture of space itself to the engines that actually light it up. Because once the universe has islands of matter, the next requirement is brutal. Stars that act like precise, long-duration power plants. Not explosions, not brief cosmic flares. Power plants that run steadily for billions of years, turning hydrogen into heavier elements and bathing nearby planets in a relatively constant stream of energy. Too short a lifetime and planets never cool, oceans never form, biology never gets beyond the molecular doodling stage. Too unstable, and any fragile chemistry is erased by radiation and violent swings in temperature. Now, let's begin. Stellar lifetimes are not arbitrary. They are set by the same forces already tuning the expansion of the universe: gravity, the strong nuclear force, the weak force, and electromagnetism. Gravity pulls the gas inward, raising temperature and pressure. The strong force lets protons stick together once they're close enough. The weak force controls how easily protons transform into neutrons inside fusion reactions. Change any of these, even a little, and you change how fast a star burns its fuel. Mass then amplifies the effect. Double a star's mass and you don't just double its brightness. You can increase its luminosity by more than a factor of 10 and slash its lifetime from billions of years down to a few 100 million. The most massive stars in the observable universe live for only a few million years before detonating as supernovae. Great for forging heavy elements quickly, terrible for giving planets a stable, long-term environment. At the other extreme, very low-mass stars can sip their fuel for trillions of years. On paper, that sounds perfect. But many of these red dwarfs unleash powerful magnetic storms and flares, especially when young. Their habitable zones are so close in that any Earth-like world would be tidally locked, with one face in perpetual day and the other in endless night, repeatedly blasted by stellar wind and radiation. In between these two regimes, something remarkable appears. A narrow band of stars with masses not too large and not too small. No one expects this middle ground to be special when you first write down the equations. No one predicts that a star with about one solar mass will have a main sequence lifetime of roughly 10 billion years and a radiation output calm enough for chemistry to slowly climb toward complexity. Our sun sits right in that Goldilocks zone. Its gravity is strong enough to ignite fusion, but not so strong that it rips through its fuel. The strong and weak forces are tuned so that hydrogen fusion proceeds at a leisurely pace, converting only a tiny fraction of the sun's mass each billion years. That slow burn gives planets time to form from the protoplanetary disk, to cool, to hold on to atmospheres, and to ride out the early violence of a young solar system. By the end of tonight, you're going to understand why this is not guaranteed. In many hypothetical universes with slightly different constants, gravity might be too weak to ever compress gas into ignition, or too strong so that every star burns like a cosmic blowtorch and dies young. The strong force might be weaker, making fusion nearly impossible, or stronger, causing almost all hydrogen to fuse in the first generation of stars, leaving little fuel for long-lived suns. In those universes, you might get brief, spectacular fireworks. You might get heavy elements sprayed into space, but you probably do not get billions of years of quiet, stable illumination on the surface of a rocky world. The boundary between star that lives long enough for oceans and star that dies before microbes finish their first experiment is razor thin in parameter space. And the Sun is not operating in isolation. Its long lifetime only matters because planetary orbits remain stable, climates remain within a certain range, and radiation levels stay low enough for fragile molecules to survive. The next layer of fine-tuning moves from the star to the planets themselves, how far they sit, how they spin, and how their internal engines recycle and protect their surfaces. No one anticipates how many separate coincidences have to line up just to keep a world like Earth habitable for more than a geological blink. Those planets and their delicate orbits are only half the story, because a perfectly placed world is useless if it's built out of the wrong ingredients. Tonight, we're going to follow those ingredients back to the only factories that can make them: stars. The early universe is simple, too simple. After the Big Bang cools, there is hydrogen, a little helium, and almost nothing else. No carbon for cells, no oxygen for water, no silicon for rocks, no iron for blood. Every complex atom in your body has to be manufactured later, deep inside blazing stellar cores that never see the surface of any planet. Now, let's begin with stellar nucleosynthesis, the quiet engine behind almost everything you see. In the core of a young star, gravity squeezes hydrogen so hard that nuclei fuse into helium, releasing energy that pushes back against collapse. That balance between gravity and fusion is as critical as any orbital distance. Too weak a strong nuclear force, and hydrogen never fuses. Too strong, and it all burns too fast, leaving no long-lived stars to host planets or life. As stars age, the story escalates. In more massive stars, when hydrogen runs low, the core contracts and heats, and helium begins to fuse. Helium can combine into carbon, then into oxygen, neon, magnesium, silicon, and all the way up to iron in an onion-like sequence of burning shells. Each layer runs a different nuclear mission, building a heavier element than the one below it, until iron marks a hard boundary where fusion no longer pays its energy bills. Buried inside that sequence is one of the most fragile balances in the entire universe, the triple alpha process. 3 helium nuclei, 3 alpha particles, have to collide in just the right way to make carbon. The only reason this works at all is that carbon has a specific excited resonance level tuned to match the combined energy of those helium nuclei. Shift that resonance by a few %, and scientists calculate that stars would produce far less carbon or far less oxygen. No one predicts chemistry like ours in a universe where one of those elements is missing. But iron is not the end of the periodic table. It is the trigger. When a massive star builds up an iron core, fusion shuts down, gravity wins, and the star collapses and explodes as a supernova. In that brief, violent moment, and in neutron star mergers far beyond our solar system, elements heavier than iron, gold, uranium, iodine, many metals life quietly depends on, are forged and hurled into space on shock waves of stellar wind. By the end of tonight, you're going to understand that carbon's flexible bonds, oxygen's role in water and respiration, magnesium in chlorophyll, iron in hemoglobin, all trace back to these cosmic furnaces operating within razor-thin physical constraints. The next question is brutal. Once those elements are scattered into space, how does a solar system like ours collect them, sort them, and turn them into a living world instead of a dead rock? Those elements don't just need to exist. They need a home, a stable address in space where a solar system can quietly assemble, run its chemical experiments, and not be erased every few million years. Now, let's begin with the largest neighborhoods of all, galaxies. Tonight, we're going to zoom out and ask a brutal question at galactic scale. Are most galaxies even capable of hosting life for billions of years? Or are they more like cosmic war zones where planets never get a chance? By the end of tonight, you're going to understand why the Milky Way's structure and even our exact address inside it are not trivial details. Galaxies come in wildly different forms. Ellipticals are giant, rounded swarms of stars, often with very little cold gas left. They had intense early star formation, burned through their fuel fast, and now mostly coast along with aging stars and harsh radiation fields. Irregular galaxies are chaotic, twisted by collisions and tidal forces, with clumps of furious starbirth and violent stellar deaths. Spirals, like the Milky Way, sit in a delicate middle ground. Organized disks, sustained star formation, and a mix of young and old stars that can support long-term habitability. But even inside a single galaxy, location is destiny. In very dense regions, galactic centers, compact dwarfs, or the crowded cores of globular clusters, stars are packed so tightly that supernovae, gamma-ray bursts, and intense ultraviolet radiation are common. Each blast can strip atmospheres, sterilize surfaces, or destabilize planetary orbits. No one expects a fragile biosphere to survive repeated hits over billions of years. Move too far the other way, into the thin outskirts, and a different problem appears. The radiation calms down, but the chemistry goes wrong. There, stars formed from more pristine gas, with fewer heavy elements. Rocky planets need carbon, oxygen, silicon, iron, products of earlier generations of stars, too metal poor, and you get a solar system of ice and gas with few solid worlds for life to stand on. The Milky Way's spiral structure threads between these extremes. Our solar system orbits in a relatively quiet suburb between major spiral arms, far from the energetic central bulge and far from the sparse, metal-poor halo. The local star density is low enough that close stellar encounters are rare, but high enough that previous generations enriched our region with heavy elements. It's a compromise. Enough metals to build complex planets, not enough chaos to constantly reset them. This is where the idea of a galactic habitable zone comes in. Too close to the center, and gravitational tides, supernovae, and black hole activity push conditions beyond survivable boundaries. Too far out, and you lose the heavy elements needed for Earth-like planets and complex chemistry. In between lies a ring, broad, fuzzy, but real, where solar systems can form, keep their orbits, and remain relatively shielded from galactic violence. Here's the pattern interrupt. This isn't just about galaxy shape. The same fine-tuned cosmic parameters that set the strength of gravity, the behavior of dark matter, and the clumpiness of the early universe also decide how many galaxies end up in that sweet spot between sterile emptiness and lethal overcrowding. Change those initial density fluctuations or the cosmological constant, and you don't just rearrange pretty spiral arms. You erase or distort the very zones where long-lived, metal-rich, stable systems can arise. So the path to a living world runs through a narrow galactic corridor, not too big, not too small, not too violent. The next question is even more precise. Inside that safe ring, how does a single solar system achieve the orbital stability, gentle radiation, and long-term energy supply that complex life demands? So the path to a living world runs through a narrow galactic corridor, but that corridor still holds hundreds of billions of possible suns. Tonight, we're going to zoom in on just one. Because out of all those stars, the one at the center of this solar system turns out to be weirdly normal in exactly the right ways. Now, let's begin. The Sun is a G-type main sequence star, a yellow dwarf in astronomers' catalogues. On the full spectrum of stellar types, it sits between the massive, short-lived blue giants and the tiny, cool red dwarfs that dominate the galaxy. Most stars are smaller and cooler than the Sun. Red dwarfs alone make up perhaps 3/4 of all stars. By simple counting, the Sun looks average, but its details tell a different story. Start at the top end. Very massive stars live fast and die violently. They burn their fuel in a few million to tens of millions of years, then collapse and explode as supernovae. The blast floods nearby space with radiation and shock waves. Those shock waves can strip atmospheres from planets, scramble orbits in young systems, and bathe everything in high-energy particles. No one expects complex ecosystems to assemble under a sky that detonates every few million years. So perhaps life should prefer the quiet majority, red dwarfs. They sip fuel so slowly they can shine for trillions of years, far longer than the current age of the universe, but their habitable zones hug the star so closely that any Earth-like planet would likely become tidally locked, with one face in perpetual day and the other in endless night. Worse, young red dwarfs unleash powerful flares and bursts of high-energy radiation. For a planet pressed up against that boundary, those outbursts can erode atmospheres and sterilize surfaces. The Sun occupies a middle ground, not too massive, not too small. Its habitable zone lies at a comfortable distance, where a rocky world can host liquid water on its surface without being tidally frozen or fried. Its output varies, but not wildly. Over billions of years, the Sun has shown relatively low variability, with a magnetic activity cycle that waxes and wanes over about 11 years instead of lurching into constant chaos. By the end of tonight, you're going to understand why that calm matters. Complex life needs time. Time for chemistry to explore possibilities, for evolution to iterate, for climates to stabilize. A star that flares unpredictably or dies young cuts that mission short. There is more. The Sun is middle-aged, about 4.6 billion years old, with billions more to go. Its metallicity, astronomers' term for the abundance of elements heavier than helium, is high enough to build rocky planets and complex chemistry, but not so extreme that it radically alters stellar behavior. Among G-type stars, that combination of age, composition, and long-term stability is far from guaranteed in a random sample. No one predicts, and absolutely no one anticipates, that a universe governed by simple physical laws will casually produce a star that threads so many needles at once. Yet here it is, shaping a stable bubble of space where a small blue planet can quietly assemble oceans, continents, and observers who ask why it all worked. The next step is to examine that planet itself and the chain of coincidences that turned a generic rocky world into a home. A star that threads so many needles is only half the story. The other half is where, in that star's light, a planet can actually stay wet, not for a season, for billions of years. Now, let's begin. Scientists call it the classical circumstellar habitable zone, the range of distances from a star where a planet with an Earth-like atmosphere could maintain liquid water on its surface over long timescales. Too close, and oceans boil into steam. Too far, and even the air can freeze. On simple diagrams, it looks like a neat green ring around a star. In reality, it is a moving, fraying boundary in a hostile cosmos. The key is luminosity. A dim red dwarf wraps its planets in a tight, close-in habitable zone. A bright blue star pushes that zone far out. And stars do not sit still on the main sequence. Over hundreds of millions to billions of years, they brighten, slowly, inexorably. As the power output rises, the habitable zone marches outward, like a receding shoreline. A world that starts in the safe band can be left behind. By the end of tonight, you're going to understand why that drift turns just right into just barely. Venus and Earth are the case study written into our own solar system. Venus orbits only about 30% closer to the Sun than Earth. On paper early on, it may have brushed the inner edge of the habitable zone. Some models suggest it could even have had shallow oceans. But as the young Sun brightened, solar energy at Venus crossed a critical threshold. Water vapor, a powerful greenhouse gas, built up. The surface heated, more water evaporated, and a runaway greenhouse took off. Oceans, if they existed, were lost to space. What remained was a dense carbon dioxide atmosphere and clouds of sulfuric acid. Earth lives just a little farther out, in a narrower corridor where greenhouse gases and clouds can stabilize temperatures instead of detonating them. Carbon dioxide, water vapor, and clouds trap enough heat to avoid a global snowball, but not so much that the oceans boil. Feedbacks between rock weathering, volcanism, and biology act like a planetary thermostat, adjusting atmospheric carbon over millions of years. But distance alone is not destiny. Planetary factors squeeze and stretch the effective habitable zone, change the atmosphere's composition, and the same orbit can swing from frozen to inferno. Increase albedo with bright clouds or ice, and a planet reflects more solar energy, shrinking the warm region. Alter rotation rate, and you change wind patterns, cloud cover, and how heat is moved from day to night. Strong greenhouse feedbacks can widen the zone slightly. Weak ones can make it razor thin. The tidy classroom ring fractures into a patchwork of climate outcomes. For complex life, the requirement is harsher. A planet has to ride inside this shifting band for hundreds of millions, even billions of years, while its star brightens and its own interior cools. That demands a delicate interplay between stellar evolution and planetary climate regulation, a long, unbroken negotiation between space and rock and air. No one expects that negotiation to go smoothly. No one predicts that a planet will hold the line for eons. And absolutely no one anticipates what happens when the habitable zone keeps drifting. But the planet refuses to give up. Because the next question is brutal. How did Earth stay temperate while the Sun's power climbed by roughly 30%? And how long can that balancing act last? So far, you've watched Earth negotiate with a brightening star. But that balancing act only works if the stage itself doesn't collapse. If the orbits of the planets go bad, climate, chemistry, even continents get reset by gravity's tantrums. Now, let's begin with the layout. The inner solar system holds 4 small, rocky planets moving on nearly circular tracks: Mercury, Venus, Earth, and Mars. Beyond the asteroid belt, 4 giants dominate: Jupiter, Saturn, Uranus, and Neptune. For billions of years, those worlds have traced almost the same paths in almost the same plane, with only slow, predictable shifts. That quiet regularity is not guaranteed by any law. It's an outcome. Tonight, we're going to zoom out and ask a brutal question. What happens in most possible solar systems? When scientists run computer missions with slightly different starting conditions, same number of planets, similar masses, just nudged orbits, the result is often not calm. Giant planets tug on smaller ones, resonances build up, and over tens or hundreds of millions of years, trajectories twist into chaos. Worlds spiral inward, collide, or get flung into deep space. Habitable zones are crossed, then abandoned. The contrast is sharp. Expectation, gravity plus many planets equals long-term instability. Reality. Our system has stayed relatively well behaved for over 4 billion years. That stability gives oceans time to persist, atmospheres time to evolve, and biology time to climb, from microbes to minds. At the center of this orbital ballet sit Jupiter and Saturn. Jupiter holds more than twice the mass of all the other planets combined. Saturn adds its own enormous pull. Their orbits lock into gentle resonances, rhythmically exchanging angular momentum instead of tearing the system apart. In the early disk, those giants sculpted the distribution of rock and ice, starving the inner region of excess material while still leaving enough to build a sizable Earth with iron, silicates, and water. They also act as partial guardians. Many comets and asteroids falling toward the inner system feel Jupiter's gravity first. Some are deflected into harmless orbits, some are ejected entirely, thinning the flux of catastrophic impactors that would sterilize surfaces and reset evolution. The shield is imperfect, but without it, the bombardment record could look very different. Here's the pattern interrupt. Change Jupiter's mass by a modest factor, or slide Saturn inward by a few percent, and long-term simulations go wild. Resonances shift, eccentricities grow. Inner planets start trading energy until one crashes into another or is hurled outward. No one expects a thriving biosphere to survive repeated planet-scale collisions. Exoplanet surveys confirm this is not just theory. Many discovered systems host hot Jupiters, giant planets parked scorchingly close to their stars on tight, often eccentric orbits. To reach those positions, they likely migrated inward through the disk, scattering smaller worlds, swallowing building blocks, and erasing the calm, temperate lanes where an Earth could quietly orbit. By the end of tonight, you're going to understand that orbital stability is not background scenery. It is an active, fragile condition. And the next question is even harsher. Once a planet has a stable path, how do its internal engines keep that world geologically alive long enough for complexity to bloom? Orbital stability gives a planet a lane to run in. But that lane only matters if the runner is extraordinary. And in this solar system, one world rolled a cosmic natural 20. Now, let's begin with the obvious, because the obvious is already improbable. Earth orbits in the narrow habitable zone on a path that is almost perfectly circular. Not wildly stretched, not plunging in and out of extremes, but close enough to the sun for liquid water, far enough to avoid a runaway furnace. The result is not perfection, but moderation. Summers and winters, not steam baths and cryogenic nights. Then there is size. Too small, and a planet bleeds atmosphere into space, its internal heat fading quickly, its surface locked into geologic silence. Too large, and gravity hangs onto a suffocating envelope, like a mini Neptune or a super Venus, where crushing pressure and toxic clouds erase oceans before they begin. Earth sits in between, massive enough to hold air and water, light enough to avoid burying them under a choking shroud. That balance feeds everything else. A thick yet transparent atmosphere filters ultraviolet radiation, spreads heat around the globe, and carries a dynamic wind system that smooths temperature extremes. Abundant liquid water covers most of the surface, storing heat, driving a planetary-scale water cycle, and enabling complex chemistry that scientists still struggle to fully understand. The surface is not a frozen fossil. It is mobile. Plate tectonics slowly rearrange continents, recycle carbon into the mantle, and build mountains that weather down, buffering the climate over millions of years. Beneath that, a hot, convecting core powers a strong magnetic field. That field pushes back the solar wind, carves out a protective bubble, and prevents the atmosphere from being stripped away like Mars once was. The boundary between Earth and space is not just altitude, it is an active electromagnetic shield. And then, high above, a companion that no one predicts for a planet this size, a freakishly large moon. Born from a colossal impact, it stabilizes Earth's axial tilt, preventing wild, chaotic swings that could drive the climate from deep freeze to global desert in geologically short bursts. The tides it raises stir the oceans, mix nutrients, and may have sculpted early coastal environments where life first diversified. Timing matters just as much as ingredients. For billions of years, Earth's climate has wandered, but within limits. Ice ages advance and retreat. Warm periods bloom and fade. Yet there is no permanent snowball, no global sterilization, no Venus-style runaway that boils the oceans. The planet stays in a metastable zone where life can adapt, recover, and innovate. Some of these traits might be common in isolation. Many planets will sit in habitable zones. Many will have atmospheres. Some will have magnetic fields or plate tectonics, or large moons, but all of them, together, tuned to the right ranges and sustained over billions of years on one world. No one expects that to be trivial, even in a galaxy with hundreds of billions of planets. So a question hangs over every exoplanet catalogue. Are observers living on an outrageously lucky world, the jackpot of this particular solar system, or are current surveys still underestimating how many Earth-like combinations the universe can assemble under the same physical laws? Before we get started on answers, the next step is to zoom out again and ask whether the apparent perfection is in Earth or in the universe that built it. If Earth feels suspiciously perfect, the moon is where that suspicion turns into a full-blown mystery. Our planet did not just get a convenient nightlight. It ended up with a freakishly large guardian that quietly rewrites the rules for climate, oceans, and time itself. Now, let's begin with scale. The Moon is about a quarter of Earth's diameter and orbits at just 384,000 kilometers. In a solar system where most moons are tiny pebbles compared to their planets, this is wild. Pluto and Charon are a binary pair. Earth and the Moon are only a step behind. No one expects a rocky world in the habitable zone to haul around a companion this big. Yet here it is. The leading origin story is violent. Early in Earth's history, a Mars-sized body slammed into the young planet. The impact ejected molten rock into orbit, stripped much of Earth's first atmosphere, and mixed the interior like a cosmic blender. That orbiting debris disk cooled and coalesced into the Moon. The mission that followed was not planned, but it was decisive. A single collision reshaped our boundary conditions for habitability. That oversized companion then went to work on Earth's tilt, Our planet is tilted about 23.5 degrees relative to its orbit around the Sun. That tilt gives seasons. The Moon's gravity acts as a stabilizing torque on Earth's equatorial bulge, damping large, chaotic swings. Simulations where the Moon is removed show axial tilt wandering tens of degrees, even flipping over on million-year timescales. The result would be extreme climate swings, ice caps migrating to the equator, tropical zones freezing, and long-term ecosystems constantly reset before complex life can dig in. With the Moon, those variations are modest. Over tens of thousands of years, the tilt wobbles a few degrees, enough to modulate ice ages, but not erase continents of biodiversity. By the end of tonight, you're going to understand that stable seasons for hundreds of millions of years is not a generic planetary feature. It is a luxury. Then there are the tides. The Moon's gravity pulls on Earth's oceans, raising bulges that race around the globe as the planet spins. On the early Earth, when the Moon was closer and tides were stronger, shorelines were chemical playgrounds. Pools filled and evaporated, concentrating molecules, cycling them through wet and dry phases that many scientists suspect were crucial for the origin of life and its first tentative steps from sea to land. Today, tides still matter. They help drive ocean circulation, mix nutrients, sculpt coastal ecosystems, and influence where heat and carbon are stored. They are a quiet planetary engine, powered by a neighboring world. And then there is the eerie coincidence. The Moon is about 400 times smaller than the Sun and about 400 times closer, so from Earth they appear nearly the same size. That's why solar eclipses can perfectly cover the Sun's disk. No one predicts that an arrangement tuned for climate stability would also generate one of the most dramatic sights in the sky. Absolutely no one anticipates that those eclipses would later let scientists probe the solar atmosphere, test gravity, and refine models of the Sun's wind. Is this all just one extravagant accident or a hint that planetary systems capable of complex life have to thread a very narrow needle? To answer that, the next step is to leave the Moon behind and ask whether the real fine-tuning lies not in a single impact, but in the deep laws of the universe that made such an impact possible at all. To answer that, the view has to zoom inward again, from orbital mechanics and impacts to something far quieter and far more critical, an invisible force threading through space, wrapping the whole planet. No one predicts that your ability to breathe owes its existence to a slow churning of molten metal thousands of kilometers beneath your feet. Now, let's begin. Earth lives inside a giant invisible magnetic bubble. It is not painted on the sky. It is generated deep inside the planet, where a shell of molten iron and nickel in the outer core is slowly convecting and spinning. That motion turns the entire world into a dynamo, a self-sustaining generator that behaves, on the outside, very much like a bar magnet tilted relative to Earth's spin axis. From space, this field pushes back against the Sun's wind. Charged particles streaming out from our star at hundreds of kilometers per second slam into the magnetic boundary, the magnetopause, and are forced to flow around it instead of straight into the atmosphere. By the end of tonight, you're going to understand that this is not a cosmetic detail. It is a shield that decides whether a planet keeps its air or has its sand blasted away. Most of those particles never reach you. Some are funneled along magnetic field lines toward the poles, spiraling down into the upper atmosphere. There, they collide with atoms of oxygen and nitrogen, dumping energy and making the sky glow. The auroras are not just a light show, they are a visible trace of a constant, ferocious interaction between the solar wind and the geomagnetic field, a battle that plays out every minute of every day. Pattern interrupt. Imagine the same solar system, the same sun, the same distance, but no global magnetic field. That is Mars. Evidence suggests that early in its history, Mars had a molten core and a dynamo. Then the planet cooled. The core largely solidified, the dynamo shut down, and the shield collapsed. With no global field to deflect or channel the wind, the upper atmosphere was exposed, and over hundreds of millions of years, the solar wind stripped most of it away. Orbiting spacecraft have watched this erosion in progress. So Earth's shield is not guaranteed. It depends on deep planetary properties, a core that is large enough to stay partially liquid, that convex vigorously, and a rotation rate fast enough to organize that motion into a coherent dynamo. Too small a planet, and the core cools too quickly. Too different a composition, and the right kind of metallic, conducting layer never forms. In both cases, long-term atmospheric retention and surface habitability are at risk. Tonight, we're going to treat that as one more clue, because the same fine balance that keeps Earth's core moving and its magnetic field alive points to something even deeper. The way the universe set the rules for how planets cool, spin, and generate fields in the first place. That same hidden engineering runs right up into the air you're breathing. Because if Earth's core and field are the invisible armor, the atmosphere is the razor-thin life support system wrapped around it. Tonight, we're going to stand on that boundary and see just how narrow the margin really is. Now, let's begin. From the ground, the sky looks like empty blue space. In reality, it's a layered mix of gases stretching hundreds of kilometers above the surface. Down where you live, nitrogen dominates, making up about 78%. Oxygen takes another 21%. The remaining sliver, less than 1%, is a cocktail of argon, carbon dioxide, methane, and water vapor. That trace fraction sounds negligible. It is not. Those trace gases are climate control. They trap some of the infrared radiation Earth emits, creating the greenhouse effect. Without it, the average surface temperature would plunge to about -18 degrees Celsius. Oceans would freeze. Weather would nearly stop. Complex life relying on liquid water and stable chemistry would struggle to gain a foothold. With no greenhouse effect, you do not get forests, cities, or spacecraft exploring the solar system. But push the greenhouse effect too far, and the same mechanism turns lethal. Venus shows the extreme. Its thick carbon dioxide atmosphere piles on over 90 times Earth's surface pressure. Temperatures soar above 450 degrees Celsius. Lead melts. Clouds of sulfuric acid drift overhead. Liquid water cannot survive. The mission outcome there is simple. No stable oceans, no breathable air, no you. Surface pressure is the other knife edge. Too low and liquid water either boils away or never melts in the first place, as on Mars, where a thin atmosphere and weak greenhouse effect leave most water locked as ice or transient frost. Too high and crushing pressures and intense greenhouse heating erase the gentle gradients complex ecosystems need. The window that allows rivers, rain, and lungs is narrow in both composition and weight. Here's the twist. Life did not just adapt to this balance. Life helped create it. Early Earth's atmosphere held almost no oxygen. Photosynthetic microbes flooded the air and oceans with it over hundreds of millions of years, turning a toxic mix into something organisms could breathe and using that oxygen to build high-energy metabolisms. At the same time, long-term carbon cycling, volcanoes emitting CO2, rocks and oceans drawing it down, acted as a slow planetary thermostat. By the end of tonight, you're going to understand that this balance is not static. It is dynamic and precarious, maintained by geological outgassing, biological feedbacks, and the changing output of the sun. No one predicts that three independent systems, rock, water, and life, would cooperate for billions of years to keep temperatures within a narrow band, yet that is exactly what Earth has discovered how to do. And absolutely no one anticipates that this atmospheric knife edge is itself set by deeper cosmic rules, the properties of matter, radiation, and gravity that determine which planets can ever hold such a sky in the first place. The sky's knife edge is not held up by air alone. It rests on rock, on a slow, grinding planetary engine under your feet that never sleeps. Tonight, we're going to dive into plate tectonics, the planet-sized thermostat that has quietly guarded Earth's climate for billions of years. From orbit, continents look frozen in place. In deep time, they drift like rafts on a slow stone ocean, colliding, rifting, and plunging back into the interior. Now, let's begin. Earth's outer shell is broken into rigid plates floating on a convecting mantle. Hot rock rises, cool rock sinks, and that slow circulation drags plates apart at mid-ocean ridges, while other plates are forced down at subduction zones. Oceanic crust is created, spreads, ages, and is recycled into the mantle, while continents ride along, crashing together to raise mountain ranges, then eroding back toward the sea. This restless surface is wired directly into the climate. When fresh rock is pushed up on continents, rainwater and weak acids attack it, grain by grain. Chemical weathering pulls carbon dioxide out of the atmosphere, locking it into carbonate minerals that wash into the oceans. There, these carbonates settle onto the seafloor, are carried on moving plates, and eventually drag down into the mantle at subduction zones. Over millions of years, volcanoes return that buried carbon to the air. The result is the carbonate-silicate cycle, a planetary feedback loop that acts as a long-term thermostat. If the planet warms, weathering speeds up, drawing down more CO2 and cooling the climate. If the planet cools, weathering slows. CO2 from volcanoes accumulates, and the planet gently reheats. By the end of tonight, you're going to understand that this slow rock cycle is as important for habitability as the solar energy pouring in from space. But this mission only runs at all because of a fragile balance. Plate tectonics needs enough internal heat to keep the mantle convecting, but not so much that the crust melts into a stagnant lid. It needs a crust that is thick enough to form continents, but thin and dense enough in the oceans to dive back down. It needs a mantle with just the right viscosity, so plates can fracture and slide. And it needs liquid water to seep into faults, weaken minerals, and lubricate subduction zones. Change those parameters, and the whole system stalls. In our own solar system, Mars seems to have cooled and frozen into a single, rigid shell. Venus, similar in size to Earth, appears locked in a stagnant lid regime, with heat building up until the surface catastrophically overturns. No one expects these neighboring planets to share the same physics, yet end up with such different tectonic lives, but that is what spacecraft observations have discovered. Without active global plate tectonics, Earth's CO2 might have remained trapped in the atmosphere, driving a Venus-like hothouse, or been locked permanently in rocks, plunging the planet into a global snowball. In both extremes, the window for complex life would slam shut, and absolutely no one anticipates how many deeper cosmic coincidences had to line up just to give Earth this delicate engine of drifting continents in the first place. Plate tectonics gives you moving continents and a long-term climate thermostat. But that thermostat only works because there is something to move heat around, something that covers most of the surface, hides in the air, and seeps into rock. Tonight, we're going to look at the most underestimated player in this entire cosmic mission, water. On paper, water should be boring. 2 hydrogens, 1 oxygen, a tiny molecule in a vast solar system. In reality, it behaves like a rebel. It has a high heat capacity, meaning it can absorb huge amounts of energy without swinging wildly in temperature. Oceans act like giant thermal batteries, buffering day against night, summer against winter, and turning what could have been a planet of brutal extremes into one where complex ecosystems can survive. Then there is the ice trick. Most liquids get denser as they freeze. Water does the opposite. It expands, floats, and forms an insulating lid. If ice sank, lakes and oceans would freeze from the bottom up, locking away liquid water and killing off most marine life during deep freezes. Instead, a thin, frozen shell protects the liquid below, keeping a reservoir of habitability even during global cold spells. Water is also an extraordinary solvent. It pulls ions from minerals, carries nutrients, and enables the chemistry of life to happen not just in one place, but across entire continents. It dissolves, transports, and redeposits, linking rock, atmosphere, and biology into a single circulating system. And its liquid range sits right in the narrow band of temperatures and pressures that a rocky planet's surface can realistically achieve. Too low a pressure, and water boils away. Too high, and it can become a supercritical fluid. To keep oceans on the surface, you need the right atmospheric pressure, the right greenhouse effect, and a star whose output does not swing too violently. No one predicts that getting just liquid water would require so many boundaries to line up. Abundant surface water is not guaranteed even in a water-rich solar system. A planet too close to its star can undergo a runaway greenhouse, where water vapor becomes a powerful greenhouse gas, the surface overheats, and the upper atmosphere is stripped by the solar wind. Too far out, and water is locked as permanent ice with barely a transient melt. So, where did Earth's water come from? Before we get started on exotic explanations, current evidence points to a mixed history. Some water was probably inherited from the protoplanetary disk, trapped in minerals as the young planet assembled. More arrived later, delivered by water-rich asteroids and, to a lesser extent, comets flung inward by the early dance of the giant planets. Change the timing or intensity of that bombardment, shift Jupiter's orbit slightly, and Earth could have ended up parched or buried under crushing global oceans. Once here, the water cycle turns a static inventory into a dynamic engine. Evaporation from oceans and lakes carries latent heat upward. Condensation in clouds releases that heat and drops liquid back as rain or snow. Precipitation runs downhill, eroding rock, carrying dissolved nutrients to the sea, and feeding rivers that carve out habitable niches. By the end of tonight, you're going to understand that this cycle is a planetary life support system. It redistributes energy from equator to poles, softens temperature gradients, and connects every ecosystem to every other. Pattern interrupt. Imagine the same Earth, same mass, same orbit, same continents, but with the water dial nudged. A slightly closer orbit, a slightly brighter young sun, or a different configuration of giant planets stirring the solar system could have left this world as a dry desert, its rocks baked and cracked beneath a thin sky. Or a frozen snowball, oceans locked beneath miles of ice, with only feeble geothermal oases clinging to warmth. In many alternate timelines, there is no blue marble, just another silent rock drifting beyond anyone's notice. Now, let's begin to ask the deeper question: what had to happen in the wider cosmos to make even this much water on even one planet possible at all? To answer that, there's one ingredient almost everyone forgets. Not water, not temperature, time. Tonight, we're going to treat time the way scientists treat gravity or light, as a hard requirement in the mission profile for making minds. It's not enough to have a habitable planet for a few million years. Complex multicellular life needs the right conditions held steady, or at least recoverable, over hundreds of millions to billions of years. By the end of tonight, you're going to understand that your existence is not just a story of where you are in space, but when you are in cosmic history. Earth's timeline is a slow-motion epic. The solar system forms about 4.6 billion years ago from a collapsing cloud in our galaxy, a region already enriched by earlier generations of stars. For the first few 100 million years, the young planet is hammered by impacts. Oceans boil, atmospheres strip, surfaces reset. No one expects that out of this chaos, a stable cradle for life will emerge. Yet as the bombardment eases, something does emerge. Within maybe a few 100 million years, simple cells appear in those early oceans. Then, almost nothing dramatic for an astonishing span. For over 1 billion years, life remains microscopic, while the planet's interior slowly drives plate tectonics, recycling carbon, regulating climate, and keeping liquid water on the surface. Around 2.4 billion years ago, microbes discover a new trick: oxygenic photosynthesis. The atmosphere fills slowly with a gas that is both poison and opportunity. This great oxygenation event could have been a permanent catastrophe. Instead, over hundreds of millions of years, the chemistry of oceans, rocks, and air adjusts. The boundary between sterile and stable is razor thin, and yet the system hovers on the life-friendly side. Then come the close calls. Global glaciations turn Earth into a snowball, ice possibly reaching the equator. Supervolcanoes belch ash and gas, asteroids slam into the surface, mass extinctions erase most species in brutal pulses, a slightly larger impact, a few more eruptions, a longer snowball phase. Each could have reset evolution back to bacteria or ended the experiment entirely, but the mission continues. After each crash, the biosphere reboots a little more complex. Animals with hard parts, forests, dinosaurs, mammals. Eventually, a primate that can build spacecraft and ask why any of this was possible at all. Zoom out, and you see this isn't just an Earth story, it's a cosmic scheduling problem. The universe had to build long-lived stars like the Sun, with steady output over billions of years, in a galaxy whose spiral arms and supernovae don't constantly sterilize young planets with radiation. The solar system had to orbit in a relatively calm neighborhood, far from the most violent galactic regions, moving through the interstellar medium without endless storms of deadly wind and debris. No one predicts that a universe born in a fraction of a second, expanding at near light speed, will also produce worlds that can stay habitable for 4 billion years. And absolutely no one anticipates how narrow the window really is. Too early in cosmic time and there aren't enough heavy elements for rocky planets. Too late and long-lived stars begin to burn out, the fuel for chemistry fading. So here is the unsettling question. Given all of this, deep time, stable stars, quiet galactic suburbs, and a planet that survives repeated disasters without losing its oceans or atmosphere, how many worlds out there have actually had enough uninterrupted time to go all the way from blind chemistry to self-aware consciousness? Before we get started on possible answers, we need to look one level deeper. The hidden rules that set these cosmic clocks in the first place. Those hidden rules have a name, and they come with a warning. If you're not careful, you can end up reading the universe backwards. Now, let's begin with the anthropic principle. In its weak form, it sounds almost trivial. Any observation you make about the universe is automatically conditioned on the fact that you exist to make it. You only ever wake up in a region of space and time where beings like you are possible. Not because those regions are special in some grand cosmic sense, but because everywhere else there's no one around to ask questions. Take stars. You orbit a long-lived, stable, middle-aged star in a quiet patch of the galaxy. That feels lucky, but the weak anthropic principle says, of course you do. Short-lived massive stars burn out in a few million years. Their solar systems never get the hundreds of millions of years needed for complex chemistry to climb all the way to brains. Any observers that evolve will, by definition, find themselves around the patient, slow-burning stars that give life enough time. No one expects to wake up in a system that never had a chance. The same logic can deflate other coincidences. You see a planet with liquid water, a magnetic field, plate tectonics, and a relatively calm impact history, and it feels like a string of miracles. But imagine billions of planets with different spins, different moons, different orbits. The weak anthropic principle says you only ever see the subset where those dice landed in the narrow range compatible with long-term habitability. The rest are silent worlds, beyond any mission, with no one to notice how close they came. Then there's the strong anthropic principle, and this is where things get more dramatic. It doesn't just say you find yourself in a life-friendly region. It says the universe must have properties that allow life to develop at some stage. Some scientists interpret that as a deeper constraint on physical law itself. Among all the ways a solar system or a cosmos could have been, only those with the right balance of forces, constants, and initial conditions are even on the table. To many ears, that feels unsatisfying. It risks collapsing into, we're here because we're here, a closed loop, a cosmic shrug. But when combined with real models that predict whole families of possible universes with different values for gravity, the cosmological constant or the strength of the nuclear forces, anthropic reasoning turns into something sharper. It becomes a selection effect you can analyze, a filter that picks out which regions of a vast cosmic landscape could ever host spacecraft, scientists, and late-night questions about why anything exists at all. By the end of tonight, you're going to understand why that move is crucial. Because to actually use anthropic arguments, you need more than one possible universe on the menu. You need variation. You need a place where the dials can slide. And that's where the story leaves the familiar solar system behind and heads into far stranger territory, the multiverse, and a landscape of realities no one predicts, but some equations almost demand. Now, let's begin. The move is bold. Instead of one perfectly tuned universe, imagine space itself as a vast cosmic field of trials. Our observable universe is just one bubble in a much larger reality, a tiny region in an enormous system where the rules are not fixed once and for all, but can vary from place to place. Different bubbles, different settings, different particles, different strengths for gravity, even different amounts of dark energy. This is the basic multiverse idea, not a science fiction escape, but a proposal that drops out of serious equations. In many models, the same physics that ignites our Big Bang does not turn off everywhere at once. Inflation, the ultra-rapid expansion that smoothed and stretched the early universe, keeps going in other regions. Some patches stop inflating and cool into bubble universes. Other patches keep inflating beyond their horizons, spawning more bubbles. Tonight, we're going to step into that picture. In this view, the mission is no longer just to understand one cosmos, but to understand a whole distribution of possible cosmoses scattered through an inflating background like islands in an endless sea. Here is where fine-tuning looks different. In a single universe story, the fact that the strong nuclear force can't be 2% weaker or 2% stronger without wrecking chemistry feels impossible to explain. The fact that the cosmological constant seems tuned to about 1 part in 10 to the 120, so galaxies can form, looks outrageous. But in a multiverse, those are not miracles. They are selection effects. If there are unimaginably many universes with different constants, observers only ever wake up in the rare bubbles where stars live long, planets can form, and complex chemistry has time to play. The cosmological constant is the sharpest case study. Before it was measured, some scientists tried an anthropic argument inside a multiverse. In most universes, dark energy is so large that the expansion tears matter apart before galaxies can condense. Only in the thin band, where the constant is small, but not necessarily zero, can galaxies, stars, and eventually life appear. Prediction versus observation. When the value was finally discovered, it landed right in that life-friendly band, small enough for galaxies, not vanishingly small. Pattern interrupt. This is not a comfortable move. It trades a single uncanny universe for a possibly infinite, unseen population. No one expects that to end philosophical debates. No one predicts it will satisfy everyone who wants a deeper reason for the numbers. By the end of tonight, you're going to understand why some scientists see the multiverse as an elegant extension of cosmic evolution, and others see it as moving the mystery up a level. Because now the question becomes, why does this larger system exist at all? And why does its landscape of possibilities look the way it does? To tackle that, the story has to leave observation's safe harbor and sail closer to the boundary between physics and metaphysics. Out here, at the boundary between what can be measured and what can only be imagined, the fine-tuning question forks into several radically different paths. Each one keeps the same data, the same eerie precision of cosmic settings, but tells a different story about why the universe looks so perfect for life. The first path says there is no luck. The constants that look like free dials, gravity's strength, the cosmological constant, the balance of the nuclear forces, aren't optional at all. They're fixed by a deeper law, a more fundamental theory that hasn't been discovered yet. In this view, asking why the gravitational constant isn't a little stronger is like asking why the number 2 isn't 2.1. It can't be. It's determined by the underlying mathematical architecture of the system. This deep law picture has a certain clean elegance, It promises that if scientists could push beyond today's physics, beyond the standard model, beyond current ideas of quantum fields and curved space, those razor-thin ranges for galaxy formation and long-lived stars would fall out automatically. No roulette wheel, no cosmic lottery, just one logically necessary universe with one logically necessary set of constants, and life as a consequence, rather than a surprise. The second path leans into the opposite idea. The constants really can vary, but the cosmos is far bigger than the visible patch around our solar system. In a multiverse, space could be divided into countless domains, each with different values for the same fundamental parameters. Most of those regions would be sterile. No stars or only brief, violent stars. No stable planets. No chemistry that can hold memory. But in a tiny fraction, the numbers line up just right and observers eventually appear to notice. Here, selection does the work. Of course you find yourself in one of the rare habitable pockets because there is nowhere else you could ever wake up. By the end of tonight, you're going to understand why many scientists treat this as a kind of cosmic version of living on a rare, life-friendly planet in a huge, mostly empty galaxy. A third path says that even this framing might be wrong. Maybe the way probability is being used, talking about typical universes drawn from a hypothetical distribution, isn't well defined. Perhaps the space of possible universes is infinite in a way that breaks ordinary intuition, so phrases like 1 part in 10 to the 120th don't mean what they seem to mean. In that case, the sense of shock at fine-tuning could be a mirage, created by applying everyday statistics to a domain where they quietly fail. And then, beyond these relatively sober options, there are ideas that push right through the usual scientific boundary. Simulation scenarios, where the constants are chosen by designers running a vast computation. Teleological pictures, where the universe is somehow biased toward life, as if the mission from the beginning were to produce observers. These sit far outside mainstream physics, but they're part of the wider landscape of explanations people reach for when the numbers look too perfect to ignore. No one expects all of these views to survive unchanged. No one predicts that every storyline will fit the data once better measurements and better theories arrive. But right now, no single perspective has won. Each one shifts the question in a different direction, from why this improbable combination to why this deep law, or why this multiverse, or why any system at all that can host minds asking questions. And to go further, the story has to dive back from philosophy toward the concrete machinery of stars, planets, and the narrow environmental corridors where life can actually take hold. Now, let's begin. The traditional story says, whenever humans think they're special, the universe gently corrects them. Earth is not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy is not at the center of space. This attitude has a name, the Copernican principle. You are not in a privileged place. You are supposed to be typical. Scientists take that seriously. When a mission flies a spacecraft past distant planets, the default assumption is that what it sees is not unique, just the first example of a common pattern. When a solar wind model predicts a boundary, the expectation is that the same physics applies everywhere. The Copernican mindset says, do not assume that here or now is special, but fine-tuning pushes back. If the cosmological constant were a little larger, galaxies would never condense out of the early expansion. If the strong nuclear force were a few % different, almost no complex chemistry would be possible. Out of the space of all imaginable universes, the fraction that can host long-lived stars, stable planets, and liquid water may be vanishingly small. So, in that larger space, observers are not typical at all. They live only in the rare pockets where the dials just happen to land in the narrow, life-friendly band. Tonight, we're going to put pressure on the word typical, because even inside a life-permitting universe, the chain of coincidences continues. A long-lived, quiet star, a planetary system with nearly circular orbits, a world in the right temperature range, with a magnetic field, plate tectonics, and a persistent water cycle. An unusually large moon that stabilizes the tilt and moderates climate swings. The rare Earth hypothesis says that microbial life might bloom in many places, but the path to complex, technological civilizations is a gauntlet that almost no world runs successfully. Now, zoom out to the galaxy. Hundreds of billions of stars, planets beyond counting. Yet, no unambiguous radio beacons, no engineering visible across interstellar space. This is the Fermi paradox. If planets are common and time is long, where is everybody? One possible answer is that almost every world fails one of the steps just listed. The universe can be vast, old, and full of planets, while the number of civilizations that reach the point of building spacecraft and asking these questions stays tiny. By the end of tonight, you're going to understand how this doesn't quite rescue human specialness, but it does refine it. The Copernican principle still stands in a geometric sense. Earth is not at the center of the solar system, and this galaxy is not privileged among galaxies. Yet selection effects mean that any observer will, by definition, find themselves in a region unusually conducive to life and thought. Not because the cosmos aims at them, but because only such regions can host observers at all. Before we get started on the detailed machinery of rare Earth conditions, there's a deeper twist. No one expects what happens when the logic of fine-tuning is applied, not to entire universes, but to the quiet, invisible processes inside a single, ordinary star like the Sun. Now, let's begin to zoom out. In the last section, the focus was on a single star and a single world. But that can be misleading. It feels like a one-off miracle. So the natural question is, how many tickets did the universe actually buy in this cosmic lottery? How many chances did it get to roll the dice and land on a planet where chemistry wakes up and starts asking questions? Start with scale. The Milky Way alone contains on the order of 100 billion stars wrapped in a rotating disk of gas, dust, and dark matter. And the Milky Way is only one galaxy among perhaps 2 trillion in the observable universe. Every one of those galaxies is its own sprawling system, with its own stellar populations, its own winds of gas and radiation, its own inventory of planets orbiting quietly in the dark. For most of human history, those planets were invisible. Then, in the last 3 decades, the pattern shattered. Spacecraft like Kepler and TESS, along with ground-based telescopes, have discovered thousands of exoplanets. Hot Jupiters skimming their stars, super-Earths hugging tight orbits. And crucially, a significant fraction of Sun-like stars appear to host Earth-sized planets in or near their habitable zones. Expectation: Earth is a bizarre outlier. Reality: Earth-like orbits are not vanishingly rare. That sounds like the universe is generous, but habitability is a harsh negotiator. Liquid water at the surface is only the opening bid. A planet might also need a large moon to stabilize its tilt, preventing wild swings in climate. It may need long-lived plate tectonics to recycle carbon and keep the thermostat running for billions of years. It probably needs a strong magnetic field to shield the surface from its star's charged wind. No one predicts all of those features will line up often. Each new filter slams the fraction down. From many stars have planets to some have Earth-sized planets in the right zone to a tiny subset keep stable climates for geological ages. Then, beyond that, there is biology itself, the leap from simple chemistry to self-replicating molecules, from microbes to multicellular organisms, from animal brains to technological intelligence that can build spacecraft and contemplate the solar system. Somewhere along that staircase, there may be what scientists call a great filter, one or more steps so improbable that almost no planet crosses them. Fine-tuning in the cosmic constant sets the broad boundary conditions. Fine-tuning in planetary history might be where most missions fail. And yet, tension remains. Even if only 1 in a billion planets meets all the criteria, a universe with perhaps 10 to the 22nd to 10 to the 24th planets still holds oceans of opportunity. No one expects, absolutely no one anticipates, that such a universe would produce life only once. So if the cosmos had this many chances, where is everybody? By the end of tonight, you're going to understand why that question is more than a paradox. It is a clue to where the next, even deeper filter might be hiding. So, if the cosmos had this many chances, where is everybody? One answer is unsettlingly simple. You only wake up in the few places where waking up is even possible. Imagine this. You open your eyes and you're underwater. Not drowning, breathing. There's a scuba tank on your back, a regulator in your mouth, gauges, fins, the whole mission kit. You could stare at the gear and think, what an incredible coincidence. Everything is just right. But if the tank weren't there, you wouldn't be thinking anything at all. Tonight, we're going to apply that same logic to the entire observable universe. This is what scientists call an observational selection effect. You only get to observe conditions that allow observers to exist. Everything you see is already filtered. It's like trying to understand the full solar system by only looking at planets where liquid water pools on the surface. Your data set is not random. It is biased by the requirement that you be there to collect it. Now, let's begin. When you look at the fundamental constants, the just right feeling is overwhelming. Gravity is weak enough that stars burn for billions of years, but strong enough to pull gas into galaxies. The strong nuclear force is tuned so that atoms heavier than hydrogen can form, but not so strong that all hydrogen fused away in the first seconds. The cosmological constant, the term that drives the accelerated expansion of space, appears fine-tuned to about 1 part in 10 to the power of 120. No one predicts that number from existing theory. It's not just small, it is absurdly small compared with naive quantum estimates. If it were much larger, the expansion of space would have ripped matter apart before galaxies could condense. No galaxies means no stars, no planets, no chemistry, no you. So why do you measure a value that happens to sit in the narrow band that permits structures to form? The selection bias answer is because there is nowhere else to stand. In hypothetical universes where the cosmological constant is bigger, there are no observers to notice how hostile it is. In universes where the balance of forces never lets heavy elements form, there are no planetary surfaces to gaze up from. By the end of tonight, you're going to understand that we observe a life-friendly universe is not a surprising observation. It is a precondition for making any observations at all. But here is the boundary of that explanation. Selection effects can tell you why you shouldn't be shocked to find yourself in a region of reality where life is possible. They do not tell you why any life-permitting regions exist within the larger space of possibilities. They shift the question. They don't erase it. So the real puzzle becomes sharper. Are these eerie coincidences simply telling you that your theories are incomplete? Are they hinting at deeper structure in the laws of nature or at a vast multiverse where different regions of space realize different constants and only a few produce observers? No one expects that debate to end soon, and the next step is to ask, how would you even test such ideas trapped in one tiny cosmic scuba bubble of reality? Trapped in that tiny scuba bubble, something else happens. The moment you hear that gravity, electromagnetism, and the nuclear forces had to land within razor-thin ranges for life, it doesn't feel like a neutral data point. It feels like a message, as if the entire universe quietly conspired so you could be here, right now, listening to this. Tonight, we're going to lean into that feeling for a moment because it is powerful. If the strong nuclear force were just a couple of % weaker, only hydrogen would exist. If it were a couple of % stronger, almost all hydrogen would have fused away in the early universe. No long-lived stars, no rich chemistry, no planets like Earth. By the end of tonight, you're going to understand why that emotional pull is so strong and why physics itself doesn't actually say the cosmos was aiming at you. Human brains are pattern detectors running at full throttle. On the ancient savannah, hearing rustling in the grass and assuming intention, a predator, an enemy, a hidden threat, was a survival strategy. No one predicts the wind. But minds that treated random noise as possible agency survived more often than minds that waited for proof. That same wiring now looks up at a solar system with just the right planets, the right star, the right boundary conditions after the Big Bang, and instinctively whispers, "This was done on purpose." This is why a freakishly large moon looks less like an accident and more like a sign. Earth's axial tilt is stabilized by that moon. Without it, the planet's orientation could wander chaotically, driving extreme climate swings that might crush complex life. Plate tectonics recycles carbon and keeps temperatures in a habitable range. A magnetic field shields the atmosphere from the solar wind. Stack enough of these coincidences and absolutely no one anticipates that the default reaction will be just chance. But here is where the discipline of physics draws a hard line. The equations do not contain goals. The cosmological constant appears fine-tuned to about 1 part in 10 to the 120 power, yet in the formalism, it is simply a parameter. The speed of light, the charge of the electron, the strengths of the forces, these enter the theory as numbers to be measured, not intentions to be decoded. The mission of scientists is to discover relationships, symmetries, and deeper laws, not to assign motives to space itself. That doesn't mean everyone stops at the equations. Some philosophical and religious traditions look at fine-tuning and see purpose, a cosmos designed with life in mind. Others point to multiverse ideas or undiscovered physics and argue that a naturalistic universe can still generate observers without any cosmic plan. The crucial point is that the same data, those delicate balances in the early universe and in our solar system, can be read in more than one way. The numbers do not force a single story, so viewers are left holding two ideas at once, The universe may not have been made for you in any literal sense, yet the fact that you can sit on a small planet orbiting an ordinary star and reconstruct how narrow the path to your own existence was is still astonishing. It is impersonal physics that feels deeply personal. Now, let's begin to ask a harder question. If the cosmos doesn't aim at you, why can your limited brain reach out across billions of light years and understand it at all? That reach is only possible because a long chain of cosmic conditions lined up before any brain, or even any star, existed to notice. Tonight, we're going to pull that chain tight and see what perfect really means when scientists say the universe is finely tuned for life. Start at the deepest layer, the fundamental constants and forces, gravity, electromagnetism, the strong and weak nuclear forces, even the tiny cosmological constant that drives cosmic expansion. The strengths of these, the mass of the electron, the charge of the proton, the speed of light, all sit in narrow ranges. Change gravity by a part in 10 to the 60 power, and the whole cosmic expansion history shifts. Make the strong force a few % weaker, and almost no elements beyond hydrogen form. A few % stronger, and nearly all hydrogen fuses too early. No long-lived stars, no complex chemistry, no solar system like yours. Then there are the initial conditions. The early expansion rate had to balance the density of matter to within about 1 part in 10 to the 60 power to avoid instant recollapse or a featureless, rapidly thinning space with no galaxies. Tiny fluctuations in that primordial plasma had to be just right, not so small that gravity never gathered planets and stars, not so large that space broke into black holes and violent clusters. By the end of tonight, you're going to understand that Big Bang was not one magic shot, but the opening move in a mission of constraints. Those constraints echo forward into galaxy and star formation. Long-lived, stable stars like the Sun only exist because nuclear physics and gravity cooperate to allow billions of years of steady fusion. The same reactions that keep a star shining also set how carbon and oxygen are forged in stellar cores and supernovae. That's one dial controlling 2 requirements at once, the fuel that lights your sky and the elements that build your body. Around those stars, planetary systems form. Orbits must be stable over billions of years. The habitable zone has to fall where chemistry can run, liquid water, not permanent ice or steam. No one predicts in advance that a planet with the right size, composition and distance will also acquire a magnetic field, an atmosphere with just enough greenhouse warming and a long-term water cycle. Yet Earth did. Some of this looks linked and law-like. Other pieces look like historical accidents. A giant impact likely created a moon that's unusually large for a rocky planet, helping stabilize Earth's axial tilt and climate. Plate tectonics may depend on initial water content, internal heat, and crust composition that could easily have gone another way on a different world. So, perfect does not mean flawless or designed in a human sense. It means that in a high-dimensional space of possibilities, many independent sliders land in overlapping narrow bands that allow complex structures, long-lived energy sources, and evolving chemistry. Before we get started on deeper explanations, picture replacing a single dial labeled Life with a vast control panel. Dozens, maybe hundreds of sliders, force strengths, particle masses, expansion rate, fluctuation amplitude, star formation efficiency, planet spacing, impact history, ocean depth. The life-friendly region in that control room is not a neat box. It is a tiny, twisted volume threading through parameter space, where stellar lifetimes, element production, orbital stability, climate regulation, and biological timescales all intersect. Our universe and this particular solar system occupy one narrow corridor through that maze. Pattern interrupt. Now imagine most of those sliders set differently. Not by a lot, just enough that stars live for only millions of years, or never make carbon, or never form planets with stable climates. In those universes there is still space, still energy, still motion. But there are no questions, because there are no question askers. The next challenge is obvious. Is this intricate alignment a deep necessity, a selection effect, or something stranger? Now, let's begin to explore how scientists try to answer that without assuming the conclusion. To push this further, there's a deeper mystery hiding in plain sight. Where does the universe end and you begin? At what point does the grand architecture of space hand off to the messy particulars of history? Before we get started, draw a line in your mind. On one side are the laws that, as far as scientists can tell, hold everywhere in the observable universe. On the other side are the accidents, the local twists and turns that played out only here. The value of the fine structure constant, for example, doesn't care about continents or climates. It sets the strength of electromagnetism from one end of the cosmos to the other. But the shape of Africa, the Himalayas, the exact path of the Nile, those are the frozen traces of plate tectonics and chance impacts on a single, small world. Tonight, we're going to stand right on that boundary, because a huge fraction of what makes you possible is already written into deep physics. The periodic table exists because quantum mechanics and the strong and weak nuclear forces allow stable nuclei all the way up through iron and beyond. The fact that atoms have discrete energy levels, that electrons don't spiral into nuclei, that chemistry can even exist at all, those are consequences of constants like Planck's constant and the electron's charge. Long-lived stars are another example. Given gravity, the speed of light, and the strengths of the nuclear forces, stars settle into a narrow band of masses that can burn steadily for billions of years. Too small, and fusion never ignites. Too large, and the star tears through its fuel in a few million years and dies in violent winds and explosions. The sun's gentle, sustained output is not random. It's a direct expression of those underlying equations. By the end of tonight, you're going to understand that even your breathing depends on this. Carbon and oxygen were forged in earlier generations of stars because the strong nuclear force is tuned so that helium nuclei can fuse into carbon instead of skipping straight past it. If that resonance had been off by a few percent, there might be no carbon chemistry, no water-based life, no planets with biospheres to explore. But then there is the other side of the line. The particular evolutionary path that led from single-celled microbes to primates to humans is not written into the fine structure constant. No one predicts the exact asteroid that ended the dinosaurs. Absolutely no one anticipates the precise timing of ice ages, the branching of hominid lineages, or the cultural explosion that produced radio telescopes and interstellar spacecraft. Both levels matter. Change the laws, and maybe no complex life anywhere. Change only the local history, and perhaps there is life, but not this life. Minds, but not these minds. So here is the unsettling question. If the universe were rewound with the same laws but different random seeds, would any observers still emerge? And would they look back at their own narrow escapes and call the universe perfect in a completely different way? So, if a single re-roll of cosmic dice could give minds that call a different universe perfect, what does that say about how much is really understood? To answer that, it helps to remember something humbling. For most of history, humanity did not even understand its own backyard. Before we get started on other universes, go back to the late 1970s. The solar system looks tidy on paper: 4 giant planets, a thin sprinkle of moons, a smooth, expanding solar wind fading gently into interstellar space. Scientists draw clean diagrams with neat boundaries and simple magnetic fields. Now, let's begin the reality check. 2 small spacecraft, Voyager 1 and 2, are launched on a modest mission, Jupiter and Saturn. 5 years. Then silence. No one expects active volcanoes on Io, blasting sulfur hundreds of kilometers high. No one predicts Europa's fractured ice hinting at a hidden ocean. Absolutely no one anticipates Triton, orbiting Neptune backwards, with nitrogen geysers erupting on a frozen world. The surprises keep coming. Titan, once imagined as a hazy rock, turns out to have a thick nitrogen atmosphere and a methane weather cycle, with liquid hydrocarbons pooling into lakes and rivers. Uranus and Neptune, predicted to be bland ice giants, reveal supersonic winds, turbulent storms, and moons with broken, stitched-together terrains. The simple solar system collapses into a messy, dynamic, layered system that no textbook had prepared for. And then there is the edge. Models say the solar wind should slow and terminate around 75 to 90 astronomical units. The heliopause, the boundary with interstellar space, around 90 to 100. Instead, Voyager 1 crosses the termination shock at 94 astronomical units, and the heliopause far beyond that at 121. Voyager 2 crosses at different distances again. The shape is not a neat sphere. The magnetic field twists in ways theory did not predict. The space beyond is both thinner and more structured than anyone imagined. This is not a minor correction, it is a warning label. If the edge of the heliosphere could not be predicted from first principles, how confident should anyone be about mapping the full space of possible universes, or measuring exactly how fine the fine-tuning really is? Every time the data get better, the pattern repeats. Exoplanets were expected to look like the solar system. Instead, there are hot Jupiters skimming their stars, super-Earths with no local counterpart, tightly packed systems defying old formation models. The cosmic microwave background confirms a flat universe and tiny primordial fluctuations, but also hints at anomalies and unexplained alignments. Particle physics nails the standard model's predictions, yet leaves dark matter, dark energy, and the exact value of the cosmological constant as deep puzzles. So some apparent fine-tunings may someday fall to deeper physics, the way planetary orbits fell to gravity and space-time. Others may remain brute facts, or clues that this universe is one region in a larger multiverse, selected because observers can arise here. By the end of tonight, you're going to understand that the real Voyager lesson is not that everything is explained, it is that the mission is still in its opening chapters. Because if 2 aging spacecraft could overturn expectations about the local boundary of space, what will the next generation do to ideas about the boundary of reality itself? So, here is the twist. Almost no one predicts. After all those delicate numbers, after all those cosmic coincidences, the story is not just that the universe allows observers. Under the right conditions, the universe may almost be compelled to produce them. Before we get started on what that means for you, zoom out. Given a cosmos with stable matter, with long-lived stars quietly burning for billions of years, with space for planets to cool and oceans to form, and with time for chemistry to climb step by step into complexity, something like life may not be a bizarre exception. It may be what happens when energy, matter, and time are allowed to play a very long game. Life, in this view, is not a thing. It is a process. A planetary scale mission that captures energy and information and refuses to let them go to waste. On Earth, sunlight and geothermal heat drive this process. Cells act like microscopic spacecraft, taking in energy, storing it, and using it to build structures that remember the past and test possible futures. DNA is not just a molecule, it is a hard drive written by 4 billion years of trial and error. Step by step, those structures become more elaborate. First simple membranes, then nervous systems, then brains that can model the environment, predict seasons, anticipate predators, plan migrations. Consciousness, in this frame, is a particularly intricate form of modeling, where the system not only tracks the world, but tracks itself, tracking the world. The universe, through you, runs a simulation of the universe. Tonight, we're going to treat that as a clue to the fine-tuning puzzle, the same constants that keep atoms from flying apart, that let the strong nuclear force be strong enough to build carbon, but not so strong that all hydrogen vanishes, also make it possible to have open-ended, information-processing structures. If gravity were tuned differently by even 1 part in 10 to the power of 60, the solar system might never have formed stable planets. If the cosmological constant were much larger, expansion would tear matter apart before a single galaxy condensed. The universe had to thread a narrow boundary between eternal chaos and eternal simplicity. That is what perfect really means here. Not perfect in the sense of designed for humans, but perfect in the sense of permitting complexity to arise, persist, and look back. No one expects a random set of equations to generate beings that ask where those equations came from. Yet that is exactly what was discovered. Now, let's begin to redefine us. On one hand, you are fragile, contingent, a product of a particular planet in a particular solar system with a particular moon that stabilizes its tilt. Change any of those details, and you are gone. On the other hand, given a universe with these laws and this much time, something that can think, wonder, and launch spacecraft beyond its own star may be almost inevitable. Holding that tension between accident and inevitability is part of the wonder. Because if life is the universe looking at itself, then every question you ask is the cosmos trying to understand its own mission. And that raises a deeper problem. Once the universe wakes up in this way, what is it supposed to do next? If the universe is awake now, the obvious next question is, how easily could this have failed? Tonight, we're going to tour the timelines where the cosmos never quite makes it to consciousness, where a single dial is nudged and everything familiar vanishes. Now, let's begin. First stop, a universe with gravity turned up just a little. Not twice as strong, not a cartoon exaggeration, but a tiny fractional increase in the strength of the gravitational force. The expectation is simple: more gravity, more structure. The reality is brutal. Matter collapses too quickly, forming stars that are monstrously massive and violently short-lived. They burn through their fuel in a few million years, explode, and leave behind black holes and neutron stars. The cosmic landscape becomes a graveyard. There is almost no time for stable planetary systems to form, no long, quiet eras where complex chemistry can patiently explore its options. Slide the dial a different way. Imagine the same space, the same initial explosion, but with a larger cosmological constant, dark energy with just a bit more push. This constant controls how fast the fabric of space itself expands. Increase it slightly, and the expansion outruns gravity everywhere. Before the first galaxies can condense, the distances between clumps of matter grow too fast. No spirals, no clusters, no web of galaxies, just a thin, cold fog of hydrogen and helium, stretching and dimming into an ever faster night. The sky is not just dark, it is empty of structure. There is nowhere for planets to orbit, nowhere for oceans to form, nowhere for questions to be asked. Change the rules again. This time, weaken the strong nuclear force, the interaction that glues protons and neutrons together in atomic nuclei. Make it only a few percent weaker, and suddenly almost no nuclei heavier than hydrogen are stable. Stars can shine, but they cannot forge carbon, oxygen, or iron in their cores. The periodic table collapses to a single note. Chemistry still exists, but only in the simplest possible molecules. No complex proteins, no DNA, no rocky planets rich in minerals. By the end of tonight, you're going to understand that without that delicate nuclear balance, the word element would mean almost nothing. So far, these dead ends play out on cosmic scales beyond any single solar system, but the fine-tuning continues all the way down to worlds like Earth. Consider a version of this planet with no magnetic field. The solid core never stirs into a dynamo. The invisible shield never switches on. The solar wind, charged particles streaming outward from the sun, slams directly into the upper atmosphere for billions of years. Gradually, that atmosphere is eroded, stripped away into space. Radiation at the surface climbs. Ultraviolet light and energetic particles break apart molecules faster than life can repair them. Oceans slowly evaporate and their water is split by sunlight. The hydrogen escaping to space, the oxygen reacting with the crust. The result is a dry, irradiated world under a harsh, unfiltered sun. No one expects that a planet can look almost exactly like Earth in mass and orbit, yet be utterly hostile because an invisible magnetic boundary is missing. Each of these timelines is only a small tweak away from the one you inhabit. Stronger gravity, a slightly bigger cosmological constant, a weaker strong force, a silent core. No one predicts, and absolutely no one anticipates how narrow the life-friendly corridor really is until the equations are written down and the simulations run. Out of an enormous space of possible universes and planetary systems, most end in sterile simplicity or violent collapse. The path that leads to oceans, to brains, to spacecraft leaving their home star is a thin thread through a maze of dead ends. And that raises an even sharper puzzle. If the odds of hitting this thread are so low, what does that say about the deeper structure of reality? That sharp puzzle is where your journey through cosmic history pays off. Tonight, we're going to pull back and look at what you now understand that most of the universe never will. From the first 10 to the power of minus 43 seconds after the Big Bang, through the birth of galaxies and stars and planets, all the way to Earth's oceans and atmosphere and cities and spacecraft, you've followed a single thread. How a violent beginning became a place that can notice it happened. Now, let's begin with the very start. In that unimaginably early moment, the universe had to get its density and expansion rate balanced to within about 1 part in 10 to the power of 60 of critical. too dense and gravity crushes everything back down before a single star ignites. Too thin, and expansion tears matter apart so quickly that galaxies never condense. You've seen how inflation smoothed space while seeding it with tiny quantum fluctuations, ripples that later grew into the web of galaxies stretching across the observable universe. You've walked through the narrow windows for the strengths of the fundamental forces. If the strong nuclear force were about 2% weaker, only hydrogen would exist. If about 2% stronger, almost all hydrogen would have fused away in the early universe, leaving no long-lived stars. Gravity had to be weak enough for stars to burn for billions of years, yet strong enough to pull gas into those stars in the first place. Electromagnetism had to allow stable atoms and complex chemistry. No one predicts that so many independent dials would land in the life-friendly range, but they did. You've seen how the cosmological constant sits at a value that looks absurdly special. Change it by about 1 part in 10 to the power of 120, and galaxies never form. How a tiny matter-antimatter asymmetry may be 1 extra particle of matter for every billion pairs annihilated, left just enough material to build planets and people. By the end of tonight, you're going to understand that every breath depends on that razor-thin excess. You've followed the chain from stellar lifetimes to habitable zones, long-lived, stable stars, planets with nearly circular orbits in just the right band where liquid water can exist. An Earth whose magnetic field deflects the solar wind so the atmosphere isn't stripped away. Plate tectonics recycling carbon, stabilizing climate over hundreds of millions of years. A freakishly large moon that steadies Earth's tilt, preventing chaotic swings that could freeze and fry the surface in wild cycles. No one expects all of these planetary and stellar coincidences to line up in one solar system. Absolutely no one anticipates that on at least one world they would lead to nervous systems, to language, to instruments that can measure the afterglow of the Big Bang itself. Here is the meta lesson. Existence, as you now see it, is not a simple given. It is the outcome of a long, contingent, finely balanced mission that began before atoms existed and continues as solar systems age and galaxies collide. Only recently have scientists been able to reconstruct this story with precision, turning ancient light and tiny particles into a coherent narrative. And that gives you a strange, almost unsettling privilege. Most of the universe is dark, cold, and unaware. Vast regions of space will never host a single conscious observer. But you, right now, are part of the tiny fraction that can look back across 13.8 billion years and recognize the boundary conditions that made you possible. The real question is what to do with that knowledge, because once you see how fragile this thread is, a deeper possibility opens up that changes what fine-tuned might actually mean. The real question is what to do with that knowledge, because once you see how fragile this thread is, a deeper possibility opens up that changes what fine-tuned might actually mean. The temptation is to leap to extremes. On one side, to declare the cosmic dials proven, evidence of destiny. On the other, to shrug and say it is all meaningless coincidence in an uncaring sea of space. Both reactions are understandable. Neither is required. Tonight, we're going to walk a narrower path, informed awe without illusion. Because the universe is not perfect in any moral sense. Galaxies collide, planets freeze or burn, stars explode, sterilizing whole regions of a solar system. Evolution on Earth rides on extinction, famine, and chance. This vast structure is indifferent to individual hopes and fears, yet within that indifference the laws of physics are tuned with almost absurd precision so that beauty, complexity, and understanding can erupt from a sea of hydrogen. Consider the strong nuclear force. Shift it by just a couple of percent and only hydrogen survives, or almost all hydrogen fuses away in the first minutes. No heavy elements, no rocky planets, no chemistry beyond the simplest atoms. Or the cosmological constant, if it were a fraction larger, expansion would rip galaxies apart before stars and planets could condense. These are not gentle adjustments. They are hard boundaries between a dead universe and one that can think. Here is the pattern interrupt. For all that, this does not prove a plan. It proves a filter. Out of all possible solar systems, only a tiny subset ever host long-lived stars, stable orbits, plate tectonics, and magnetic fields that shield atmospheres from the solar wind. Out of those, only a narrower subset get liquid water, a calm enough climate, and billions of quiet years for life to experiment. And out of that already microscopic fraction comes you. Every relationship, every decision, every moment of curiosity is layered on top of 13.8 billion years of expansion and cooling, of stars forging carbon and oxygen, of a particular planet in a particular system orbiting a star in a particular arm of a galaxy. No one expects a chain that fragile to lead to beings who can understand it. No one predicts that atoms tuned by impersonal equations will one day ask why those equations exist at all. In a universe where conscious life may be rare and fragile, that realization carries a responsibility. If awareness is uncommon, preserving and expanding the tiny pockets where it arises becomes a meaningful project in itself. Protecting this planet, exploring other worlds, building spacecraft that can carry our questions beyond the heliosphere. These are not just technical missions. They are ways of keeping the cosmic experiment of understanding alive. By the end of tonight, you're going to understand one more layer of that responsibility. Because one of the simplest, most powerful ways to honor this improbability is to keep learning. Through videos, books, and the work of scientists who push at the boundary of the known. Now, let's begin the final step of this journey and ask what it really means to live in a universe that almost never makes minds like yours, and did it here once. So now, after almost 2 hours tracing how fragile, contingent, and improbably aligned this cosmos is, you're still here, following the thread all the way to the edge, in a universe that could have expanded into cold, featureless darkness, or collapsed in a furious instant. Attention like that is rare. It means this wasn't just background noise, it meant something. Before we get started on closing the book, look at what that attention has already done. Tonight, we're going to treat a click, a comment, a share as part of the same story as a fine-tuned constant or a precisely balanced expansion rate. Tiny actions, vast consequences. The strong nuclear force only had to shift by a few percent to erase complex chemistry. Your decision to like this video takes far less energy than that, but across millions of curious minds, it changes which questions this channel can afford to ask next. By the end of tonight, you're going to understand that engagement isn't just a metric, it's a steering wheel. When you subscribe, when you share this with the friend who stays up at 2 a.m. wondering why anything exists at all, you are voting for more long, difficult, ambitious missions into deep time and deep space. You are telling the algorithm and the humans behind the scenes that there is an audience for episodes about the origin of time, black holes and information, and the ultimate fate of the solar system. No one expects videos this long to thrive in a landscape of 30-second clips. No one predicts that a 2-hour meditation on cosmology, philosophy, and the boundary between existence and non-existence will hold attention. And absolutely no one anticipates that the same platform delivering comedy and music videos can also sustain a community obsessed with the cosmological constant being tuned to 1 part in 10 to the power of 120. Yet here you are, and here this is. That is why likes, comments, and subscriptions matter. They are the solar wind pushing this tiny spacecraft of a channel outward, giving it the momentum to attempt riskier trajectories. With enough support, the next mission can be a full deep dive into the cosmic microwave background, reading those ancient ripples in space as a fossil record of the universe's first 380,000 years. Or a sweeping tour of exoplanet habitability, asking how many planets out beyond Neptune's quiet shadow might carry oceans, atmospheres, and perhaps minds. Or a Voyager-style case study in humility, how 2 small spacecraft showed scientists that almost every model of the heliosphere's shape was wrong. So, if this journey helped you understand your place in the system just a little more clearly, consider subscribing, leaving a thought below, and sending this to one other person who loves questions more than answers. Because in a universe that had to get so much right for you to be here at all, choosing to understand it is one of the few things that truly feels necessary. So, before this mission ends, imagine one more journey. Not with a spacecraft racing beyond the solar system, but with you stepping outside after this video ends, letting your eyes adjust and lifting your gaze to the same dark the Voyagers vanished into. Above you, points of light. Familiar, quiet, almost ordinary. But tonight, we're going to ask you to hold them differently. Not as random glitter, but as the visible tip of a chain of improbabilities so long and so precise that the fact you can stand there and notice them is already a kind of miracle. Pick one star. Anyone. Let your attention lock onto that single point, then trace it back. Behind that glow is hydrogen crushed under gravity, stellar fusion balancing collapse and explosion in a narrow window where atoms are neither ripped apart nor left forever dark. Behind that is a galaxy, a rotating system of hundreds of billions of stars sculpted from tiny ripples in the early universe that had to be tuned to about 1 part in 100 trillion. Keep going. Those ripples came from a universe that expanded at almost exactly the right rate, where the density balanced on a knife edge so sharp that a change of 1 part in 10 to the power of 60 would have meant no planets, no solar systems, no place for liquid water to collect and wait. The same story that shaped that distant star shaped every atom in your blood, your bones, the air in your lungs. Now, let the view widen. There is the moon hanging closer, and larger than moons around similar planets have any right to be. No one expects a collision early in Earth's history to produce a satellite that just happens to help steady the planet's tilt and climate. No one predicts that its pull would help drive tides that mix oceans, move nutrients, and carve coastlines where life can experiment. The next time you see that moon, remember its quiet role in your story. The next time you feel a breeze on your face, think of the atmosphere's narrow balance, thick enough to hold warmth and water, thin enough that you can still see the stars beyond it, shaped by solar wind and magnetic fields that shield you from radiation. The next time you drink water, pause on its journey, from ancient stars that forged oxygen to icy planetesimals to oceans that rose and fell over drifting continents. By the end of tonight, you're going to understand one thing in a new way. The universe did not have to be perfect for you, in any human sense. It did not have to be kind, or gentle, or even long-lived. But its laws and its initial conditions were just precise enough that, in at least one small corner, a species emerged that could send metal messengers past the heliosphere's boundary and then stand under the same sky, wondering what it all means. No one predicts that from equations alone. Absolutely no one anticipates consciousness as a side effect when protons and electrons first scatter free. Yet here you are, able to notice, able to understand, able to care. So when this ends and the screen goes dark, let there be one last transition, from pixels to starlight. Step outside if you can, look up, hold the night sky not as background, but as context. In a universe that could have been silent in so many ways, you get this, a brief chance to exist, to think, and to wonder. Use it well.